everyone! Welcome to our exciting new course on Zig programming. Get ready to dive into the world of efficient coding, where you'll master essential skills like performance optimization, safe memory management, and developer productivity. This course is jam-packed with hands-on coding exercises designed to solidify your learning. You won't just be listening, you'll be doing. So make sure to check the description for a link to our GitHub repository where you'll find all the code examples and resources to support your journey. And hey, don't go anywhere until the end because there's a final project waiting to test everything you've learned, also up for grabs in that GitHub repo. So, what are you waiting for? Let's jump right in! Zig is a general-purpose programming language that focuses on three essential pillars: performance, safety, and, of course, developer productivity. Now, imagine a language designed to help you create high-quality software without the usual headaches. Yeah, that's Zig for you. It aims to be a better alternative to C, giving developers all those features they love while still maintaining that crucial speed and control. So, whether you're diving into your first project or you're a seasoned pro looking for more efficiency, Zig offers some exciting possibilities. Let's explore what makes it stand out. Now, let's dive into an important concept in Zig: explicit error handling, using a function called safe divide. This function works with two integers, performing division, but it's got a neat twist. It checks for division by 0 right off the bat. If the divisor is 0, instead of diving headfirst into undefined behavior, this function smoothly returns an error labeled division by 0. This approach ensures that the caller has to handle this potential pitfall, reflecting Zig's commitment to safety and reliability in coding. So, when you call safe divide, remember that you must check its result. It could either be a valid integer or an error. This nudges developers towards a more mindful coding style by promoting awareness of edge cases right from the start. The error union type in Zig, which is indicated by that exclamation mark, serves as a signal for developers to be on alert for possible errors. This encourages robust error handling practices, allowing for a safer programming environment. In essence, by adopting this explicit error handling strategy, Zig empowers developers to focus on crafting functional and reliable software without the looming fear of unexpected failures due to neglected edge cases. Now, let's dive into how we can leverage Zig's powerful compile time capabilities to calculate the Fibonacci sequence. In this case, we're defining a recursive function known as Fibonacci. This function will compute the Fibonacci number for any given integer n. Remember, the base case of the recursion is critical here. It'll simply return n when it's 0 or 1, which helps us avoid getting stuck in those infinite loops. All right. Next up is the main function, where we harness the magic of @compileTime call to evaluate our Fibonacci function with the input value of 10 right at compile time. This is really cool because it allows the computation to happen during the compilation phase, which means we sidestep any runtime overhead, leading to faster execution. Once we compute the value, we can utilize Zig's built-in debugging print function to display the outcome, the Fibonacci number for 10. Now, this really illustrates how Zig's compile time features not only boost performance, but also keep your code clean and easy to read, making it a fantastic choice for applications where performance is key. And you still get to express complex logic without losing that all-important clarity. Now, let's dive into managing dynamic memory allocation in Zig. In this example, we start by obtaining a memory allocator, which allows us to allocate and free memory manually, kind of like what you do in C, but Zig comes with some added safety features. So, we're going to define the size of the array we want to create and request memory for an array of 10 U32 integers using the allocator.alloc method. This approach gives us direct control over memory, which, as you can imagine, is really crucial for performance-critical applications. Now, here's where it gets interesting. We use the defer keyword. This little gem ensures that the allocated memory is automatically freed when it goes out of scope, which minimizes our risk of memory leaks. It's a powerful feature that gives us safety while still allowing for manual management. Within a loop, we'll populate our array with the squares of their indices. This not only demonstrates how easy it is to work with pointers, but also how memory manipulation can be straightforward in Zig. Finally, we iterate through the array once more to print out those squared values. This showcases both our memory management skills and array handling all in one go. So, this example really highlights the balance that Zig strikes between control and safety in memory management. Now, let's explore how we can leverage Zig's powerful cross-compilation feature to build applications for different architectures effortlessly. When we run the command zig build xe myprogram.zig -target equals x864-linux-gnu, we're basically telling the Zig compiler to generate an executable binary from our Zig program, which is myprogram.zig. The -target flag, this is crucial, specifies the architecture and platform for which we wish to build the executable. So in this instance, x864-linux-gnu indicates that the binary we create is intended to run on a 64-bit Linux system. This flexibility, it's particularly valuable in today's diverse computing environment, where we often need software that can operate across various hardware specifications without the hassles of changing development environments. And honestly, this single command encapsulates the essence of Zig's simplicity and efficacy. It's designed to make things a breeze for developers involved in systems programming and embedded systems to work with multiple targets seamlessly. Now let's take a closer look at how this command simplifies the building process, allowing you to focus on writing code rather than worrying about environment configurations. It's all about making your development experience smoother and more enjoyable. Now, let's take a moment to explore how we can manage dependencies in Zig using its build system. To kick things off, we begin by importing two modules. One is the standard library, and the other is a hypothetical library named mylib. This is done with the @import statement, which gives us a clean and organized way to pull in the necessary modules for our project. By including these libraries, we're not only keeping our code tidy, but also making it easier to access their functions and features without adding unwanted complexity. Next up, we define the main function, which serves as the entry point for our program. Inside this function, we call the perform task method from our mylib library. This illustrates how Zig promotes modularity and encourages a clear code structure, which can really boost both productivity and readability. Finally, we employ the standard library's debug print function to send out a message that signals our task is complete. This method of managing dependencies not only streamlines our coding process, but also helps us maintain clarity and organization throughout our project. Now, let's dive into how we can define and use structs in Zig, which are super important for creating those complex data types. In our example, we start by declaring a person struct that holds two fields, name and age. This struct is like a blueprint for creating person instances, letting us group related data together in a neat and organized way. Next up, we define a method called greet right within the person struct. This method takes a pointer to a person instance as its argument, and it uses the stand.debugPrint function to share a personalized greeting that includes the name and age fields. See how this connects behavior directly to data in an object-oriented style? It really enhances the clarity and structure of our code. Now, in the main function, we create an instance of person by initializing it with specific values for name and age. Then we call the greet method on this instance, which gets that greeting message printed out. This straightforward implementation shows just how Zig's syntax allows for clear, concise definitions of both data structures and their behaviors, promoting better organization and readability in our code. Now, let's take a moment to explore how Zig's built-in testing capabilities can significantly boost the reliability of our code. In this example, we're defining a straightforward test for the safe divide function. The test lives within a test block, which we've named Simple Test. This helps clarify what functionality we're evaluating. Inside this block, we'll call the safe divide function with the arguments 10 and 2, and we're expecting the result to be 5. This really highlights how Zig enables clear and direct testing of code behavior. Now, to ensure that our test succeeds, we'll be using the try statement along with stead.testing.expect, which checks if the returned value matches our expectations. If for some reason the test doesn't pass, Zig gives us immediate feedback during compilation. This seamless integration of testing into the development workflow strengthens code quality and ensures that every change maintains the functionality we expect from our program. And you know what? By utilizing these testing mechanisms, developers can confidently evolve their code bases, secure in the knowledge that any regressions will be caught without delay. As we start wrapping up our introduction, it's worth mentioning that the community around Zig is growing rapidly. With a focus on transparency and collaboration, developers are encouraged to participate in discussions, contribute to libraries, and share knowledge. The open-source nature of Zig means that anyone can help shape its future. This vibrant community is invaluable, making learning and troubleshooting much easier. To illustrate this, you can find a plethora of resources online, such as forums, tutorials, and the official documentation that are continuously updated by both the core team and the community. So, whether you're tackling a beginner question or diving into advanced topics, you'll find support and guidance from fellow Zig enthusiasts, which is honestly pretty great. Now, let's take a look at how to compile a Zig program with optimizations for performance. The command provided instructs the Zig compiler to build an executable from your Zig source file, in this case, myprogram.zig. What's exciting here is that we're applying optimization settings specifically aimed at enhancing execution speed. By using the -o release fast option, you're telling the compiler that you want to produce optimized code that runs quickly. This is all about striking a balance between build time and application performance. It's particularly beneficial for applications where speed is really critical. With Zig, you can harness its full potential without getting bogged down by complicated or verbose code structures. The essence of this command really lies in Zig's ability to compile down to efficient machine code. This means you can write applications that perform just as well as those written in more traditional systems programming languages, like C. So, really, with minimal effort, you can position your applications for high performance while focusing on building robust logic rather than juggling intricate optimization flags. So, to wrap things up, Zig is definitely more than just a new programming language. It's a carefully designed tool that truly caters to the needs of modern developers, prioritizing safety, performance, and productivity. With features like manual memory management, expressive syntax, and an easy-to-use build system, Zig really empowers developers to create robust applications without those frequent headaches that come with other languages. You know? I really hope you're as excited as I am about diving deeper into Zig programming. So, make sure to stay tuned for more engaging content, where we'll explore even more advanced techniques and features that'll make your coding journey enjoyable and productive. Happy coding! Now let's see how we can implement error handling in Zig with a function that reads from a file. The readFile function takes a file name as input and returns either the file's contents or an error, which really highlights Zig's explicit error handling approach. Notice how we use the try keyword. This allows us to attempt to open the file, and if that fails, it immediately returns the error. No need for those cumbersome try-catch blocks. We also include a defer statement to ensure the file closes properly, which, trust me, is crucial for preventing resource leaks. Now, inside the main function, we call readFile and handle its results using a switch statement. This differentiates between specific errors, like file not found and out of memory, ensuring that potential failures are addressed directly. This is great for enhancing code reliability and clarity. If the function succeeds, we'll print the contents to the console, showcasing both successful file reading and effective error management. This is central to writing robust applications in Zig. Through this, we can really see how the language emphasizes making error handling a prominent and integral part of the development process. Now, let's take a closer look at how we can create a function in Zig that calculates the factorial of a number right at compile time. The factorial function is established through recursion, meaning it efficiently determines the factorial of a given non-negative integer. So when n equals 0, it simply returns 1, just like the math defines it. For any other number, it calls itself with n minus 1, then multiplies the result by n, allowing it to compute that factorial. To make the most of Zig's compile-time execution feature, we use @compileTime call, which lets us calculate the factorial of 5 right during compilation, rather than waiting until runtime. This effectively removes any runtime overhead, so you can enjoy faster application performance since that result gets computed before the program even runs. Finally, we're going to display our result in the console using std.debug.print, which showcases the calculated factorial value. This example cleverly illustrates how compile-time execution in Zig can optimize performance, really reinforcing the capability of the language to blend powerful functionality with enhanced efficiency. Now, let's implement an example that demonstrates Zig's manual memory management capabilities by allocating and managing a dynamic array. In the code, we start by importing the standard library, which gives us the tools we need for memory allocation. The main function begins by defining an allocator that will handle our memory requests. We specifically use the page allocator here, which is designed for those larger chunks of memory we're going to work with. All right, so next we decide how big we want our dynamic array to be, and for this example, we're setting that size to 5. After that, we use our allocator's alloc method to get memory for an array of U32 integers. Now, it's super important to handle any potential errors that might pop up during this allocation, and we can do this neatly with the try keyword. To avoid any pesky memory leaks, we employ the defer statement, which ensures that once we're done with our allocated memory, it gets freed automatically. Once we've allocated the memory, we'll fill our array with the square of each index inside a loop. Finally, we'll run another loop to print out the values we stored in the array. This not only showcases the results of our computations, but also highlights how Zig allows us to manage memory efficiently while keeping safety in mind with its handy defer feature. Now, let's see how we can compile a Zig program for different target architectures with just a single command. The command we'll be using is zig build-x myprogram.zig target equals x86-64-Linux GNU. This command really highlights the power of Zig's cross-compilation feature, allowing developers to create a binary that can run on an entirely different architecture. In this case, the x86-64 architecture designed for Linux systems. What I love about this command is its simplicity. There's no need for those headaches of complex configurations or switching between different environments, which can often be such a hassle in other programming languages. This streamlined process lets developers focus more on writing code instead of juggling multiple development setups. It's especially advantageous for projects that involve embedded systems or applications meant to work across platforms. By leveraging this functionality, developers can produce efficient binaries tailored for heterogeneous systems with minimal effort, enhancing productivity and workflow significantly. This feature truly exemplifies Zig's commitment to making cross-platform development straightforward and accessible, solidifying its status as a modern language for diverse computing needs. Now, let's dive into defining and utilizing a simple struct in Zig. In this example, we'll create an employee struct that encompasses both the name and the position of an employee. This really highlights Zig's clarity in syntax. It's straightforward and easy to grasp. The struct also comes with a method called introduce, which takes a pointer to the employee instance and uses std.debugPrint to show a message that introduces the employee by their name and position. Next up, we'll create an instance of our employee struct. In the main function, we instantiate emp as an instance of employee, providing a name and position. The clear syntax for initializing the struct really helps newcomers understand how data is organized and manipulated in Zig. Now, when we call the introduce method on this instance, we get to see the behavior tied to that data in action, which beautifully showcases the power of method integration within structs. This approach not only enhances code readability, but also illustrates how Zig balances simplicity with the ability to express complex ideas effectively. Now, let's explore how to incorporate testing in Zig, highlighting its built-in testing capabilities. To do this, we will write a simple test for an addition operation. In this example, we're going to create a test named addition that checks whether adding 2 and 3 results in 5. Here, we use the try keyword alongside stead.testing.expect, which allows us to validate that the expected result matches the actual computation of the sum. So, if this condition evaluates to false, Zig will provide a compile time error, letting us know that the test has failed. This integration of testing directly within our codebase ensures that as we modify and evolve our application, we maintain its reliability and functionality. Implementing tests alongside our regular code fosters a consistent practice, allowing for rapid validation of changes and reinforcing the overall integrity of our application as it grows. By doing this, we can trust the outcomes of our code more fully and support a culture of quality and accountability in our development process. This community surrounding Zig is really growing rapidly, and it's creating a wealth of resources and support for new learners. This thriving community, it really fosters collaboration and knowledge sharing, allowing developers at all levels to grow together. So let's dive into some popular resources where you can engage with other Zig enthusiasts. Here we go. First up, the official Zig documentation. This is your go-to guide, providing in-depth tutorials and guides. Next, we've got Zig forums and community chat rooms. These spaces are perfect for discussions and inquiries. It's like having a buddy to bounce ideas off of. And, of course, don't forget about GitHub repositories. They showcase some really exciting projects and libraries built in Zig. This vibrant environment, it makes it super easy for newcomers to find support and guidance, while also allowing experienced developers to contribute and share their knowledge, pushing both the language and community forward. It's an exciting time to be part of the Zig ecosystem. As we wrap up our exploration of Zig's key features and benefits, it's clear that Zig offers a unique approach to programming, one that really emphasizes safety, performance, and productivity. We've covered some really interesting aspects, like its strong error handling, the compile time execution, and let's not forget about manual memory management. These elements together present developers with the tools they need to create top-notch software. Now, in summary, we discussed how Zig places a priority on explicit error handling. This approach promotes stable coding practices, which, as you can imagine, is quite crucial. We've seen how compile-time execution can significantly improve performance, and how manual memory management allows developers to take full control over their resources. And of course, the syntax clarity and the supportive community really enhance the overall experience, making Zig an exciting option for modern developers wanting a robust tool to tackle their projects. Thank you for joining me on this deep dive into Zig. As you continue to explore its features, just keep experimenting and asking questions. By doing so, you're bound to uncover even more of the wonders this language has to offer. Happy coding! Zig offers a compelling set of features that make it an attractive choice for developers. Today, we're going to dive into the key features of Zig, exploring how this programming language truly stands out in terms of performance, safety, modularity, and developer productivity. So far, we've learned that Zig is a powerful programming language focusing on these essential aspects. Now, let's explore the specific features that make Zig a unique and effective tool for developers seeking a modern programming experience. From its ability to deliver bare metal performance and maintain strict safety standards, to its focus on simplicity and clarity, Zig is designed to let developers work efficiently and with ease. We'll discuss how its modular approach encourages code reuse and organization, creating a more enjoyable coding experience. Plus, we'll touch on how Zig's commitment to developer transparency empowers you to truly understand and control every part of your project. So, stay tuned as we uncover how each of these features can greatly enhance your development journey with Zig. Now, let's take a look at a simple Hello World program in Zig. This code begins by importing the standard library, which provides essential functionality for input and output operations. We define a main function, which serves as the entry point for our program. Within this function, we utilize st.debug.print to output the string Hello World, followed by a newline character. This straightforward approach really demonstrates how effortlessly Zig allows us to display text on the screen while still maintaining high performance due to its compiled nature. By directly compiling to native code, Zig ensures that this program runs efficiently, consuming minimal resources. Now, the use of the standard library in our code exemplifies Zig's design philosophy, combining simplicity with effectiveness. Executing this program showcases not only swift execution, but also highlights the low overhead that Zig offers, a crucial aspect for developers aiming to create high-performance applications. So, we've effectively utilized Zig's capabilities in a concise manner, setting the stage for exploring more complex features of the language in the subsequent sections. Next, we will write the following code to demonstrate manual memory management in Zig. In our example, we start by importing the standard library, which provides essential utilities. Now, we will define the main function where all of our memory allocation will take place. Here, we create a variable for the allocator specifically using stead.heap.pageAllocator, which allows us to request memory from the heap. Nice, right? Then, we specify the size of memory we want to allocate, 32 bytes in this case. Even though we're venturing into manual memory management, we're not going rogue. We leverage Zig's robust error handling with the catch clause. This gives us a solid fallback if our memory allocation fails, ensuring our program keeps running smoothly by printing an error message. To avoid memory leaks, a common pitfall in manual memory management, we utilize Zig's defer statement. This nifty feature automatically frees the allocated memory at the end of its scope, acting like a safety net. Finally, we print the address of the allocated memory, giving us insight into where our allocation has happened. This structure not only showcases Zig's approach to memory management, but also highlights how its features can enhance our safety and control. Now, let's take a look at a simple yet effective implementation of a function that checks if a number is even. We define a function named isEven, which accepts an integer parameter num of type I32 and returns a Boolean value indicating whether the number is even. The core logic here employs the modulo operator to determine if num is divisible by 2, returning true if it is. Next, we'll showcase how to use this function within the main function. Here, we declare a constant variable, number, and assign it the value 42. This sets up our example conveniently, as 42 is an even number. We utilize an if statement to call the isEven function with number as its argument. Depending on the result, we either print that the number is even or that it is odd. This structure really emphasizes the clarity and simplicity of Zig's syntax, allowing developers to quickly grasp the logic without getting bogged down in complex code. This clear expression of intent is one of the hallmarks of Zig, making it accessible for both newcomers and experienced developers alike.
Next, we will write a code snippet that demonstrates Zig's robust error handling capabilities. In this example, we begin by attempting to open a file named example.txt from the current working directory using the try keyword. Now, this operator is pretty important because it signals that the operation might fail and allows us to address any potential errors explicitly. If opening the file doesn't work out, execution will stop right there and the error will be returned, making it crystal clear where things went wrong. Once the file is successfully opened, we set it up to be closed automatically with the defer statement. This is crucial because it ensures that resources are managed correctly, reducing the risk of memory leaks. Next, we read the entire content of the file into memory using the try keyword again, this time with read to end alloc, which, guess what, also introduces the possibility of failure. So if reading the file doesn't succeed, we stop execution again, following that strong error handling approach Zig encourages. Finally, if both operations go smoothly, we utilize std debug print to output the file's content to the console. This whole process not only illustrates how Zig motivates developers to deal with errors right at the source, but it also highlights how the language's features promote safe and efficient coding practices. Now let's take a look at how to create and utilize a simple module in Zig. In this example, we're defining a module named math.zig, which contains a public function called add. This function takes two 32-bit integers as parameters and returns their sum. By encapsulating this addition logic within a separate module, we keep our code organized and, even more important, we enhance its reusability across different parts of our project, or even in other applications. Next, we will implement the main.zig file, where we'll import both the Zig standard library and our custom math module. So within the main function, we call the add function from the math module, passing in the numbers 5 and 7. The result of this calculation is stored in the variable result. Finally, we use Zig's built-in debug print functionality to display the output, which shows the result of the addition operation on the console. This modular approach exemplifies how Zig facilitates better organization and code reuse, making it a powerful feature for managing larger projects effectively. Now let's take a closer look at how Zig simplifies project management using its built-in build system. We can create a build.zig file to configure our project by utilizing the builder module from the standard library. This approach lets us define how our executable should be built in a well-organized way. So in this script, we start by adding an executable with a specified name, let's say my app, and we set its entry point as src/main.zig, which is where all the exciting application logic resides. Next, we indicate the target platform with native, which means we want to compile the application specifically for our host environment. This really helps ensure that the binary is optimized for the machine it's running on. Now we also set the build mode to release small, focusing on creating smaller binaries without losing out on performance. This option is especially useful when resource efficiency is top of mind. Finally, we call exe install to ensure that our executable is correctly installed, which streamlines the whole deployment process. Overall, this structured method of building projects in Zig significantly boosts developer productivity by cutting down on complexity, and giving us more time to focus on developing the application rather than managing the build process. Now let's explore how Zig handles concurrency through the use of threads. In this example, we're defining a function called concurrent task, which takes an identifier for the task and prints a message indicating that the task is being executed. This simple function sets the stage for the work each thread will perform. Now moving on to the main function, we set the number of tasks we want to run concurrently. Here we've chosen 4 tasks, Zig's std. Thread is utilized to create an array of thread handles, which corresponds to the number of tasks. Now let's implement the logic to spawn these threads. We loop over each thread handle and use the std thread spawn method to create a new thread for our concurrent task function. Inside this loop, we also handle any potential errors that might occur during the thread creation, ensuring robustness in our program. Finally, to maintain the integrity of our program, we join each thread back to the main thread. This ensures that the main execution waits for all concurrent tasks to finish before proceeding. This demonstrates how Zig allows for efficient task handling in a concurrent environment, making it easier to maximize application performance through parallel execution. Finally, let's touch on the open source nature of Zig and how, the community really drives its ongoing development. This transparency allows developers to dive deep into the language's foundation. Additionally, it ensures that users can contribute to its evolution, which is pretty crucial given the ever-changing programming landscape. Zig has a growing ecosystem, and its community continually introduces well-maintained libraries and tools. The involvement of its users helps ensure that the language remains relevant and keeps evolving, reflecting the needs of developers worldwide. In summary, we've explored Zig's core features. We've got strong performance through native code compilation, safe memory management practices, a clear and concise syntax, explicit error checking, powerful modularity, and enhanced developer productivity with a robust build system. Oh, and let's not forget about efficient concurrency support. Plus, there's that supportive, community-driven development model. As Zig continues to develop, its ecosystem represents an exciting avenue for developers seeking performance and safety in their programming. Whether you're transitioning from C or venturing into systems programming for the first time, Zig stands as a compelling choice worthy of your consideration. Zig's history and philosophy are rooted in a desire to create a performant, safe, and productive programming language. While the modern programming landscape is filled with numerous options, Zig really stands out. It focuses on principled design and clarity, aiming to fill those gaps left by existing languages. So far, we've learned that Zig is indeed a powerful programming language that emphasizes performance, safety, and modularity. It achieves those high execution speeds through native code compilation, while employing manual memory management for better control and safety. Oh, and let's not forget the clear syntax and robust error handling, which really enhance developer productivity and facilitate efficient concurrency. Plus, Zig's open-source nature fosters this amazing community that contributes to the language's growth and relevance in the programming landscape. Now let's dive into the history and philosophy behind Zig. We'll explore its development, the motivations of its creators, and how these elements shape the language today. Zig was created with a vision in mind, to offer developers a tool that combines the high performance of C with modern features found in newer languages, like Rust. The language emerged from the experiences of its creator, Andrew Kelly, who sought a solution to the many frustrations encountered while working with C and C++. Developers often faced unknown behaviors, memory safety issues, and cumbersome syntax, which made productive development quite the challenge. Zig aims to remedy these challenges by providing a simple and predictable environment, allowing programmers to concentrate on crafting efficient and maintainable code. One of the reasons Zig has resonated so well with developers is its fascinating journey from a mere idea to a fully fledged programming language. Kelly started developing Zig back in 2015, and you know what triggered it? His experiences with traditional systems programming languages. They can be quite challenging. He aimed to create a compiler that didn't just translate code into machine instructions, but also made debugging and maintaining that code so much easier. And so the first version of Zig was born, simple yet powerful. Since then, it's been on a path of continuous development and improvement, all while staying true to its core philosophy. Now, this evolution was significantly shaped by community feedback, which really highlights the open-source nature of Zig. By being open source, Zig fosters collaboration and builds this thriving ecosystem where developers can contribute to its growth. Isn't that great? This community-driven approach has led to regular enhancements, making Zig even more robust over time. Different modules and libraries created by the community are now available, allowing developers to build on existing resources and share their experiences with the language. It's pretty inspiring to see how far it's come. Now let's take a look at a simple implementation of the Fibonacci sequence using a recursive function in Zig. The Fibonacci function we're defining here demonstrates a classic recursive algorithm. It takes an unsigned 32-bit integer parameter, n, and returns the Fibonacci number corresponding to that index. Within the function, we check if n is less than or equal to 1. If it is, we simply return n, as the Fibonacci values for both 0 and 1 are the same as the input. For values greater than 1, the function makes two recursive calls, one for n1 and another for n2, effectively breaking down the problem into smaller subproblems. This showcases how recursion can simplify the expression of logic in a clear and concise manner. Next, we observe the main function, which serves as the entry point of the program. Here we define a constant, num, set to 10, which represents the Fibonacci index for which we want to compute the value. We then call the Fibonacci function with this index, storing the result in the result variable. Finally, we use std debug print to output the calculated Fibonacci number, demonstrating not just the functionality of the code, but also Zig's straightforward syntax for outputting data to the console. Now let's explore how we can manage memory efficiently in Zig through a straightforward example. First, we begin by importing the standard library, which gives us the necessary functionalities we need, including memory allocation. Within the main function, we initialize an allocator from std heap page allocator, and this is crucial because it's responsible for managing our memory. Next, we define a variable called size and set it to 16, indicating that we want to allocate 16 bytes of memory. Now, when we call the allocator alloc function, we're requesting a block of memory meant to store unsigned 8-bit integers, which we represent with U8. However, keep in mind this function can return an error, so we need to handle that gracefully using Zig's error handling mechanism. This way, if allocation fails, we'll print an appropriate error message and exit without any fuss. To enhance our memory safety, we incorporate the defer keyword, which ensures the allocated memory will be freed when it goes out of scope, preventing any potential memory leaks. Finally, we print the address of the newly allocated memory, showcasing the explicit control that Zig provides over memory management. This approach really exemplifies how Zig combines performance, safety, and clear syntax, empowering developers like us to handle resources effectively. Now let's take a moment to explore how we can read from a file in Zig while carefully managing any potential errors. The readFile function kicks off by trying to open a specified file using the openFile method, and here s/zig stry keyword comes into play. This keyword is really important because it checks for errors during the file operation. If something goes wrong, execution just halts. This prevents any unintended behavior and makes any error state clear. So once we successfully open the file, the defer statement steps in. This ensures that when the file goes out of scope, it's properly closed. It's all about resource management and, avoiding those pesky memory leaks. After we've got the file open, we move on to reading its contents into memory using read-to-end alloc. And guess what? Success here is also monitored with that same trusty try keyword. If reading the content doesn't go as planned, we exit the function smoothly, without running into any confusing undefined behavior. Finally, we use std debug print to show the file content on our screen. This whole process not only demonstrates Zig's approach to file handling and error management, but also highlights how crucial clear and straightforward syntax is for enhancing our productivity and keeping our code nice and readable. Now let's implement a simple module for mathematical operations in Zig, focusing on how it enhances code organization and reuse. We begin by creating a file named math.zig, where we define a public function called add. This function takes in two integer arguments, r and b, and returns their sum, which really demonstrates Zig's straightforward syntax and ease of function definition. Next, we will create a main.zig file, where we import the standard library in our newly crafted math.zig module. Here we can see the use of import to bring in our custom module, allowing us to access its functionality seamlessly. Now within the main function, we invoke the add function from the math module, passing in two integer values, 5 and 7. The function calculates that and returns the result. The result is then printed to the debug console using std debug print. This structure not only emphasizes modularity, but also promotes a clear separation of concerns in our project, making it easier to manage larger code bases. Such modular architecture is truly a best practice in programming, helping developers maintain and refactor their code more efficiently over time. As we dive into the history and philosophy of Zig, it's important to emphasize its strong commitment to the development community. You see, Zig isn't just a tool for individual developers. It actively nurtures a collaborative environment where users are encouraged to report issues, suggest features, and even contribute code. This spirit of collaboration creates a dynamic feedback loop that's truly invaluable for the growth of any programming language. Zig's community efforts don't stop there. They extend to a wealth of publicly available resources, including extensive documentation and tutorial materials that really help newcomers get on board. The transparency and openness that the Zig community embraces means the language keeps evolving based on real-world use cases and the actual needs of developers. It's a beautiful example of how shared knowledge can drive development forward. Next, let's take a look at a simple for-loop implementation in Zig that really illustrates the language's commitment to clarity and readability. In this example, we have a loop that iterates 5 times, capturing a fundamental aspect of programming, controlling the flow of execution. So the loop starts with a variable I of type U32, and guess what? It's set to 0. Now, before each iteration, we check the condition I5, ensuring the loop only runs while I is less than 5. And inside the loop, there's a debug print statement that outputs the current iteration number. It's a great way to see how easily Zig integrates debugging capabilities. After each iteration, the increment operation I plus equals 1 kicks in and updates the loop variable, moving us closer to termination. This straightforward syntax not only makes it easy for beginners to grasp the language's constructs, but it also highlights Zig's design philosophy of dodging unnecessary complexities. By focusing on what's essential for effective programming, Zig truly empowers developers to write clean and maintainable code, all without sacrificing performance. As we wrap up our exploration of Zig's history and philosophy, it's essential to acknowledge a fundamental truth about programming languages: they continually evolve. You see, Zig's development is not static. It reflects this ongoing dialogue between its creators and the community. As technologies advance and new paradigms emerge, Zig remains adaptable, ensuring it can tackle the challenges of modern software development effectively. This added layer of community involvement means that Zig will continue to grow, receive timely updates, and adapt to the needs of the programming landscape. Now, in summary, understanding Zig's history and philosophy reveals a deep commitment to creating a language that prioritizes performance, safety, and productivity, while emphasizing developer empowerment through open-source collaboration. By stripping away unnecessary complexity and providing a clear syntax, Zig serves as a valuable tool for both experienced programmers and those just beginning their development journey. As we venture further into our exploration of Zig's features and capabilities, we will see how these foundational principles translate into real-world applications and complex programming tasks. Zig is a general-purpose programming language designed with a focus on performance, safety, and developer productivity. Let's dive into the exciting world of Zig and explore its features, benefits, and how it stands out among programming languages. So far, we learned that Zig is a programming language designed for high performance, safety, and productivity, emerging from the frustrations developers faced with traditional languages like C and C++. It combines the efficiency of native code compilation with manual memory management and a clear syntax to enhance developer experience and resource control. The community-driven development fosters collaboration, resulting in a robust ecosystem and continuous language improvement. Zig's commitment to simplicity and modularity ensures that it remains accessible and effective for both novice and experienced programmers. Now, we will explore Zig's history, philosophy, and fundamental features, which make it an intriguing choice for developers across various domains. Zig was founded by Andrew Kelly, who drew inspiration from his experience with Rust. The goal was to create a language that would address Rust's complexity while maintaining excellent performance. Zig's philosophy revolves around creating a simple yet powerful programming environment. Its development embraces transparency and open-source principles, inviting a community of contributors to steer the project's direction. This community-driven approach ensures that Zig continues to evolve based on actual developer needs and preferences. For instance, one of Zig's distinguishing design goals is its focus on performance. Zig compiles to native code, similar to C, offering speed and efficiency. However, it doesn't stop there. Zig prioritizes safety features, incorporating manual memory management along with a stronger and more intuitive type system. Surprisingly, Zig does not support garbage collection. Instead, developers manage memory allocations directly, which provides fine-grained control and minimizes overhead. Now let's take a look at a simple Zig program that provides a demonstration of basic data types and function implementation. The code begins by importing Zig's standard library with const std import std, which allows us to utilize essential functionalities such as logging. Next, we define the main function, which serves as the entry point for any Zig program. Inside this function, we declare two constants, name, representing a string value Zig, and version, holding a numeric value of type U32 initialized to 0. The use of the const keyword is significant here, as it indicates that these variables are immutable, ensuring their values cannot be changed after assignment. We then call std log info to output a formatted message, welcoming users with the specified name and version. This built-in logging feature is a straightforward way to display information and debugging data. Overall, this program exemplifies Zig's static typing, allowing developers to catch type mismatches at compile time, thus enhancing code safety and readability. Next, we will implement a function that dynamically allocates an array, showcasing Zig's manual memory management capabilities. The function createArray accepts the desired size of the array as an argument. Within this function, we utilize Zig's standard library memory allocator to allocate memory for the array of 32-bit unsigned integers. The try keyword is employed to handle any potential errors that may occur during memory allocation, ensuring that we can gracefully manage failures. After successfully allocating memory, we populate the array using a loop, where we iterate over each element and assign it a value that corresponds to its index converted to an unsigned integer. This showcases both the allocation process and the initialization of values, which is typical when working with dynamic arrays. In the main function, we call createArray to create an array of size 10. We also apply the defer statement to ensure that the allocated memory is automatically freed right after main completes execution. This is crucial in preventing memory leaks, illustrating Zig's focus on memory safety and efficient resource management. Finally, we log each element in the array to demonstrate the successful allocation and initialization of our dynamic array. Next, we will explore how to implement concurrency in Zig, showcasing the ability to run tasks simultaneously. In this example, we define a function called worker, which simulates a repetitive task by logging its name and an index value in a loop. Inside this loop, a 1-second pause is introduced between logs using the std time sleep function, allowing us to see the task's progress over time. Now let's look at the main function, where we initiate two synchronous tasks using the async keyword. This allows both worker calls task 1 and task 2 to execute concurrently. Once we start these tasks, we wait for their completion using the await keyword on both tasks. This approach elegantly handles task coordination without the complexity of manual thread management, as often seen in other programming languages. By employing this concurrency model, developers can write efficient code, achieving significant performance improvements for applications that involve multiple operations. Zig's straightforward syntax and built-in concurrency features empower programmers to create responsive and scalable applications with ease. Now let's implement a simple program that demonstrates how to handle command line arguments in Zig. In this example, we start by importing the standard library, which provides various functionalities that enhance our coding experience. The pub-fn main function is declared as the entry point of our application, indicating where the program begins its execution. Within the main function, we retrieve the command line arguments using std process args, which gives us access to any inputs passed to the program. We then perform a check to ensure that the user has provided at least one argument. If the necessary argument is missing, our program gracefully returns an error message, guiding the user to provide the required input. If an argument is present, we proceed to log that information using std log info, which outputs the provided argument to the console in a formatted manner. This not only illustrates how straightforward it is to manage command line inputs with Zig, but also highlights the language's design goal of reducing complexity for developers, allowing them to focus more on coding rather than configuration. Such ease of use ultimately fosters a smoother development experience. Now let's implement a module for mathematical operations that demonstrates the power of modularity in Zig. We will begin by creating a module that includes two fundamental mathematical functions, addition and multiplication. In Zig, we define functions using the pub-fn keyword, which signifies that these functions are publicly accessible to other files within the project. The add function takes two integers as parameters, adds them together, and returns the result. Similarly, the multiply function performs multiplication on the two integer inputs and returns the product. By encapsulating these operations in their own module, we not only promote code reusability, but also enhance maintainability. Next, we will see how we can utilize this module in our main program. By importing the mathematical module, we can call the add and multiply functions directly. This approach streamlines our code and makes it more organized. We will create a main function that computes the sum and product of the numbers 5 and 10, then log these results using Zig's standard logging capabilities. This example illustrates how modular programming allows developers to structure applications more efficiently, fostering better collaboration among team members. While we've explored various features of Zig, let's recap what we've covered so far. We started with Zig's core philosophy and how it emphasizes performance, safety, and simplicity. We walked through several code examples illustrating basic syntax, memory management, concurrency, and modularity. Through these examples, it is clear how Zig provides robust tools for developers, ensuring a productive coding environment. Now, in the next part of our lesson, we'll delve deeper into Zig's unique features, such as its interoperability with C, and examine real-world applications where Zig's performance shines. As you can see, Zig emerges as a modern programming language that successfully caters to the demands of contemporary software development. Its unique attributes, from performance optimization to developer-focused design, make it not just a tool for coders, but a powerful ally in their quest for efficient programming. In our next videos, we will explore practical applications and advanced features of Zig, ensuring that you are well prepared to harness its full potential. Get ready to dive deeper into the world of Zig. Zig offers a compelling set of features that make it an attractive choice for developers. With its focus on performance, safety, and simplicity, it addresses many of the challenges faced by programmers today. In this lesson, we'll dive deeply into these key features and benefits, showcasing what makes Zig stand out in the crowded landscape of programming languages. So far, we learned that Zig is a general-purpose programming language focused on performance, safety, and developer productivity, designed to overcome challenges encountered with traditional languages. It emphasizes manual memory management and offers a clear syntax, which aids in creating efficient and intuitive programming environments. The community-driven development approach fosters continuous improvements while ensuring that Zig remains accessible for developers of all skill levels. As we move on, we will explore Zig's unique features and real-world applications to further understand its capabilities. Now let's take a look at a simple program that demonstrates how we can measure the execution time of a function in Zig. In this example, we begin by defining a function named slowFunction that intentionally introduces a delay through an extensive loop. This simulates a computationally expensive operation, allowing us to analyze performance. Next, we move into the main function, where we utilize the std time millitimestamp function to record the current time before and after calling our slow function. This timestamping mechanism is crucial as it captures the precise duration of the function's execution. By calculating the difference between the end time and the start time, we derive the total execution time, which we then log to the console using Zig's built-in logging features. This not only showcases Zig's efficiency, but also demonstrates its ability to handle performance-critical tasks effectively. Through this program, we learn how easily we can engage with timing operations in Zig, highlighting its potential for developing high-performance applications. Now let's see how we can implement a robust error handling mechanism in Zig using the safe_divide function. This function takes two floating-point numbers as input, R and B. Before performing the division, it checks whether B is 0. If it is, the function returns an error instead of attempting the division, which would cause a runtime crash. This proactive approach allows developers to manage possible error scenarios cleanly within their code. Next, we move to the main function where we call safe_divide with the numbers 10 and 0. This example deliberately triggers the division by 0 error. We then utilize Zig's powerful switch statement to handle the outcome of the division attempt. If the function returns the division by 0 error, we log a warning message to inform the user that dividing by 0 is not allowed. Conversely, if the division is successful, the result is logged for the user to see. This clear structure not only improves code readability, but also enhances maintainability, making it easier for developers to manage errors in their applications effectively. Now let's take a look at a practical example that illustrates Zig's efficient handling of arrays and loops. In this code snippet, we begin by declaring a constant array named numbers, which contains 5 integer elements. This straightforward declaration showcases Zig's simplicity in type inference, allowing us to define the array without unnecessary verbosity. Next, we introduce a variable sum, initialized to 0, which will hold the cumulative total of the elements within the array. The heart of this example lies in the for loop, where we neatly iterate over each element of the array. This concise loop syntax highlights one of Zig's design philosophies: clarity and ease of reading. As we iterate through numbers, we increment our sum variable by each num, demonstrating how straightforward it is to manipulate array data. Finally, we utilize Zig's built-in logging functionality to display the total sum of these numbers in the console. By focusing on the logic rather than the intricacies of syntax, this example emphasizes how easily developers can perform calculations and manage data structures in Zig, aligning perfectly with the language's goal of enhancing productivity while maintaining performance. Now let's see how we can define a simple yet effective testing mechanism in Zig. We begin by creating a function named add that takes two integers as parameters and returns their sum. This straightforward function exemplifies how efficient Zig can be for arithmetic operations, ensuring clarity and performance. Next, we introduce a test block dedicated to verifying that our add function operates correctly. By naming the test add function, we ensure that it's easily recognizable within our testing suite. Inside this block, we call the add function with the arguments 2 and 3 and store the result in a variable called result. This step is crucial for validating our assumptions about the function's behavior. Finally, we utilize the std debug assert function to check if the result equals 5, which is the expected output of the addition operation. If the assertion fails, it indicates a bug or error in the function implementation. This built-in testing framework significantly enhances confidence in our code quality, encouraging a systematic approach to testing that ultimately leads to more reliable software. Now let's see how we can implement a simple program in Zig to determine the current target architecture. In this code, we begin by importing the standard library, which provides essential functionalities for logging and other operations. The main function is defined to initiate the program's execution, where we utilize Zig's built-in feature at target arch to retrieve the architecture for which the application is being compiled. This is a powerful capability that allows developers to write code that adapts seamlessly to different platforms. We then use the std log info function to print the current architecture to the console, demonstrating how easily Zig provides information about the build environment. This not only helps in debugging, but also plays a crucial role in developing cross-platform applications. The code structure remains clear and straightforward, showcasing Zig's emphasis on readability. By understanding how to access these target details, you can tailor your applications more effectively, ensuring optimized performance across varied systems. Now let's see how we can leverage Zig's interoperability with C by using the math library to perform a square root calculation. In this example, we begin by importing the standard Zig library and then utilize cimport alongside at cinclude to include the standard C math library, which provides us access to the sqrt function. Next, within the main function, we call C sqrt25 to compute the square root of 25. The ability to invoke C functions directly demonstrates how Zig allows developers to work with established C libraries seamlessly, enhancing productivity. Finally, we log the result using std log info, which prints out the square root, showcasing how easily we can call and handle C functions within Zig. This capability not only provides a smooth transition for developers familiar with C, but also facilitates the integration of existing C codebases into new Zig projects without redundancy or extensive rewrites, emphasizing Zig's strengths in combining performance with ease of use. Zig's community-driven development model also plays a significant role in its appeal. Developers can contribute to the ongoing evolution of the language by providing feedback and suggestions. Open-source projects thrive on community involvement, and Zig is no exception. The emphasis on fostering an inclusive community helps ensure that Zig evolves based on the actual needs and experiences of developers. This feedback loop can lead to rapid improvements, making the language not just a tool, but a shared project where users feel invested. As we get deeper into Zig's ecosystem, you'll often hear about its excellent documentation. Well-maintained documentation is crucial for any programming language, and Zig shines in this regard. Its user-friendly resources provide thorough explanations, examples, and tutorials that enable developers to quickly get up to speed. A specific module breakdown allows you to focus on what interests you the most without sifting through unrelated content. To summarize our exploration of Zig, we have highlighted its ability to produce optimized machine code, dynamic error handling, simple syntax, integrated testing framework, cross-platform support, interoperability with C, community-driven development, and extensive documentation. These features make Zig not just a programming language, but a comprehensive development tool suitable for a variety of applications. As we wrap up this lesson, remember that Zig is designed to make programming not only efficient, but also enjoyable. With its features tailored to enhance developer productivity while maintaining control over performance, Zig holds tremendous potential for both new and experienced developers. In our next session, we will explore more advanced topics in Zig, including its unique concurrency model and memory management capabilities. Get ready to dive even deeper into the fascinating world of Zig is a general-purpose programming language designed with a focus on performance, safety, and developer productivity. So far, we learned that Zig is a programming language emphasizing performance, safety, and simplicity, designed to tackle issues encountered with traditional languages. It features optimized machine code generation, robust error handling, clean syntax, an integrated testing framework, cross-platform capabilities, and interoperability with C. The community-driven development model and extensive documentation further enhance its appeal, making Zig a valuable tool for developers of all skill levels. Now we will delve deeper into Zig's unique features, its philosophy, and how it compares to other programming languages. Zig was created by Andrew Kelly, who previously contributed to the Rust programming language. Kelly sought to address some of the perceived complexities of Rust while maintaining a focus on performance that older languages like C provide. The result, a modern alternative that is both performant and easy to use. Utilizing Zig allows programmers to write clean, efficient code without battling convoluted syntax or extensive boilerplate. With Zig, you can expect a language that prioritizes developer productivity alongside software safety. Next, we will write a Zig program to calculate the Fibonacci sequence using a recursive function. The program starts by importing the standard library, which provides essential functionality for working with input and output. The fib function is defined to take a single argument, n, of type U32. This function will compute Fibonacci numbers recursively. If n is less than or equal to 1, it directly returns n, effectively serving as the base case for the recursion. Otherwise, it calls itself twice, summing the results of fib n1 and fib n2. In the main function, we invoke fib10 to compute the Fibonacci number for 10, demonstrating the function's ability to perform calculations efficiently. After calculating, the program uses std debug print to output the result to the console, showcasing how Zig handles console output with a simple yet effective syntax. This example illustrates not only Zig's performance in executing recursive algorithms, but also highlights its clean and straightforward approach to code structure, enabling developers to focus on the logic of their applications rather than complicated syntax. Now let's implement a snippet that showcases manual memory management in Zig. In this example, we begin by importing the standard library, which provides essential features for our program. We define the main function, where we create a variable for the memory allocator, specifically using page allocator, which is optimized for allocating larger memory blocks. Next, we allocate memory for an array of 100 U32 integers. This line demonstrates Zig's explicit handling of memory, allowing us to manage the array's size and type directly. After successfully allocating the memory, we enter a loop to populate the array with values, specifically even numbers ranging from 0 to 198. Here, you can observe how effortlessly Zig allows us to manipulate the elements within the array. Following the population of the array, we employ another loop to print each element to the console, illustrating how we can easily access and display our data. Finally, it's crucial to free the allocated memory once we finish using it. This step highlights Zig's emphasis on manual memory management and reinforces the importance of avoiding memory leaks, ensuring better control over resource management in your applications. Now let's take a look at a simple Hello World program in Zig, which serves as a foundational example of the language's clean syntax and ease of use. In this code, we first import Zig's standard library using const std import std, which provides essential functionality for input and output operations. Next, we define the main function, declared as pub_fn_main, void. The pub keyword indicates that this function is public, allowing it to be accessible from outside the module. The void type signifies that the function does not return any value. Within the main function, we utilize std debug print hello world \n to output the familiar phrase hello world to the console. The std debug print function is an efficient way to display text, and the \n character adds a line break after the output for clarity. This straightforward example showcases how Zig's syntax allows you to focus on writing logic without unnecessary complexity, making it an excellent choice for both new and experienced programmers. By starting with such a simple program, developers can quickly grasp the essentials of Zig's structure while enjoying the process of learning a new language. Now let's see how we can implement a simple modular program in Zig to add two numbers effectively. We'll start with the add.zig module, where we define a public function named add that takes two parameters, a and b, both of type U32. This function returns their sum, which demonstrates the simplicity and clarity of Zig's syntax for function definitions. Next, we will create the main.zig file, where we will make use of our add module. Here, we import the standard library in our add module. In the main function, we invoke the add function by passing in two integers, 5 and 10. The result of this addition is stored in a variable called result. Finally, we use the standard debug print function to display the sum on the console in a readable format. This modular structure not only adds clarity to the code, but also enhances collaboration within teams, as different functions can be developed and tested in isolation before being integrated into the main program, showcasing Zig's focus on modularity and developer productivity. Now let's explore a practical implementation of concurrency in Zig. We'll define two asynchronous tasks designed to run simultaneously, allowing for efficient task execution. The first task, task 1, outputs a message indicating that it is running, while the second task, task 2, does the same. Both are marked with the async keyword, signifying that they can be executed concurrently. Next, we will execute these tasks in the main function. By calling async task 1 and async task 2, we're initiating both tasks, which enables them to operate in an overlapping manner. This pattern is particularly beneficial for I/O-bound operations where waiting times can significantly hinder performance. By leveraging Zig's concurrency model, developers can enhance the responsiveness of applications, especially when managing multiple tasks that may be waiting on I/O operations. Overall, this approach not only improves resource utilization, but also showcases Zig's robust concurrency support, enabling developers to craft applications that can perform efficiently in multitasking environments. Now let's see how we can implement a simple program that demonstrates Zig's cross-platform capabilities. The code starts by importing the standard library and retrieving runtime information about the target operating system. Within the main function, the program checks which operating system it is running on by evaluating runtime targetos. Depending on the detected OS, Windows, Linux, or Mac OS, the program uses the std debug print function to output a corresponding message to the console. This design allows developers to easily tailor their applications for different environments, ensuring that the right functionality is executed without needing separate code bases for each platform. It's important to note that Zig's compile-time evaluation of the target environment enables efficient development, as there's no need for complex runtime checks. Instead, each condition is evaluated during compilation, optimizing the application for the specific target OS. By using this cross-platform approach, you can streamline the development process, making Zig an excellent choice for building versatile software. To sum up, Zig stands out as a modern programming language that values performance, safety, simplicity, and modularity. Its unique features like manual memory management, a clean syntax, and robust concurrency support contribute to its growing popularity among developers. Zig allows for efficient cross-platform development while ensuring code safety, enhancing overall productivity. In our future lessons, we will talk about advanced topics including concurrency and memory management, where we will dive deeper into how Zig handles these crucial aspects to provide even better performance and safety. Prepare yourselves for more engaging content as we explore Zig, uncover its nuances, and enhance our coding. Now let's see how we can implement manual memory management in Zig with a practical example. We begin by importing the standard library to access various functionalities, including memory allocation. In the main function, we declare an allocator using std heap page allocator, which is responsible for handling memory allocation. We set the size of our array to 10 and use the allocator to allocate memory for an array of unsigned 32-bit integers. This manual allocation allows us to retain complete control over memory usage, a key feature of Zig that contrasts with languages that rely on garbage collection. We then populate this array with values by iterating through it and assigning each element a value that is 3 times its index. This straightforward loop demonstrates how intuitively we can manipulate arrays in Zig. After using the allocated array, we ensure to explicitly free the memory by calling allocator free array, which prevents memory leaks and underscores the importance of managing memory manually in performance-critical applications. This structured approach to memory management showcases Zig's commitment to efficiency and safety in programming. Now let's take a look at a fundamental example of a Zig program that outputs "Hello World" to the console, a classic starting point for many programming languages. In this code, we begin by importing the standard library, which provides essential functionalities for input and output operations, among others. The program defines a public function named main, which is the entry point of any Zig application. Within this function, we utilize the std debug print function to display our message. This function stands out for its simplicity and clarity, taking a string as the first argument, our custom message, and a second argument that specifies formatting options, which in this case is an empty tuple. The escape sequence \n in the string ensures that the output will end with a new line, making the console output neater and more readable. This concise yet effective approach exemplifies Zig's clean and expressive syntax, allowing developers, regardless of their experience level, to grasp core concepts and begin working with the language easily. Thus, with just a few lines, we've created a functional program, reinforcing how Zig prioritizes both simplicity and productivity in coding. Now let's take a look at how Zig handles errors with explicit error handling. We begin our example in the main function where we call mayfail function, which is designed to return an error. The exciting aspect is the use of the catch syntax. This syntax allows us to gracefully capture any errors that occur during the function call. If an error arises, the program will not crash, but will instead execute the block of code following catch. Within this block, we print a clear error message, which displays the specific error that occurred. This feedback is vital for debugging and ensures that developers know exactly what went wrong. Additionally, after handling the potential error, we print the result of the function call. If mayfail function successfully completes without an error, the result is printed to the console. Notably, this approach reinforces the philosophy of safety in coding by encouraging developers to be proactive in predicting and managing errors, rather than reacting to them after they've occurred. Thus, we illustrate how Zig promotes a more careful coding practice through its intuitive error handling mechanism. Now let's see how we can implement asynchronous functions in Zig to effectively manage concurrency. In this example, we define two asynchronous functions, task1 and task2. Each function is marked with the async keyword, signaling to the Zig runtime that they can be executed concurrently. Inside both functions, simple debug print statements are included to output messages indicating when each task is running. Next, we proceed to the main function, where we invoke both asynchronous tasks simultaneously by calling them prefixed with async. This approach allows Zig to kick off each task without waiting for the other to finish, showcasing the ease with which concurrent execution can be handled. When executed, the tasks will print their respective messages to the console independently, demonstrating how easily Zig manages multiple ongoing tasks without blocking the main thread. This design not only simplifies the code, but also enhances the application's responsiveness, which is crucial in developing efficient and scalable software. Through this implementation, you can see how Zig's concurrency features empower developers to create high-performance applications with relative simplicity. Now let's see how we can implement a code snippet that showcases Zig's cross-platform capabilities. In this example, the program begins by importing the Zig standard library and accessing the runtime information. The main function is where the action takes place. Here, we check the target operating system at runtime using runtime targetos. The code employs conditional statements to determine which operating system is currently being used. Depending on whether the OS is Windows, Linux, or Mac OS, the program prints the corresponding message to the console. This modular approach demonstrates how easily developers can adapt their applications for different environments without needing to modify substantial portions of code for each platform. By utilizing a single code base that intelligently identifies the OS at runtime, developers can maintain a clean and efficient development workflow. Such flexibility is especially advantageous in today's diverse computing landscape, where applications often need to be compatible across multiple operating systems. Zig effectively streamlines this process, making it a prime choice for developers looking to build versatile and portable applications. Now let's take a look at how Zig's build system simplifies project configuration and dependency management through a straightforward setup in a build.zig file. In this configuration, we initiate the build process by importing the necessary builder from Zig's standard library, which sets the stage for creating an executable. Next, we define our project executable named example and specify its source file located at src/main.zig. By adding this executable configuration, we establish which file the compiler will compile into a runnable program. The next critical step involves setting the build mode to standard release options, ensuring that our application is optimized for performance when compiled. This option reduces overhead, resulting in faster execution speeds, which is essential for production environments. Finally, we call the install function on our executable instance. This function handles the installation of the built executable to an appropriate location, making it readily accessible for execution. This clear and organized configuration exemplifies how Zig's build system aids developers in efficiently compiling and managing projects, allowing them to focus on writing robust code while maintaining clean project structures. As we dive deeper into Zig, it's essential to recognize its growing community and excellent documentation. An active community contributes to the development of libraries, tools, and best practices, making it easier for newcomers to find their footing. Meanwhile, the official documentation is rich, offering comprehensive resources that guide users through various aspects of the language, from getting started to advanced techniques. The community-driven approach not only enhances the language itself, but also allows developers to share knowledge, solve problems together, and push Zig forward. As examples, you'll find numerous forums and repositories online where both new and experienced developers exchange experiences, tips, and code snippets. As we conclude our exploration of Zig's features, it's clear that the language is a powerful candidate for a wide range of development projects. With manual memory management, clean syntax, robust error handling, strong concurrency capabilities, and cross-platform support, Zig enables developers to create efficient, safe, and modular applications that meet today's demanding performance standards. So far, we've learned about Zig's design principles and features that make it engaging and practical for developers. In future lessons, we will delve deeper into advanced topics, particularly focusing on concurrency and memory management, to further enhance your coding journey in Zig. Get ready as we uncover the intricacies of these essential components and solidify your understanding of this exquisite programming language. Zig is a general-purpose programming language designed with a focus on performance, safety, and developer productivity. It strives to combine the efficiency of low-level languages like C with the safety and ease of higher-level languages. In this lesson, we'll embark on an exciting journey to understand the core concepts that make Zig a compelling choice for developers. So far, we learned that Zig offers a range of attractive features for developers, including performance, safety, simplicity, and modularity. We explored its manual memory management, clean syntax, robust error handling, concurrency support, and cross-platform capabilities. These elements make Zig an effective choice for creating efficient and reliable applications. In the upcoming segments, we will discuss how to write and compile Zig code, examine its syntax, and learn about its error handling mechanisms. Now let's see how we can verify our Zig installation. To do this, we will use a simple command in the terminal, which is zig version. This command checks whether the Zig compiler is correctly set up and accessible from your command line. When you run this command, if everything has been installed properly, it will return the current version of Zig that is installed on your system. This step is essential because it confirms that the compiler is ready for use, allowing you to start developing your application seamlessly. Ensuring that your development environment is correctly configured is a foundational part of working with any programming language, including Zig. Verifying the installation lets you proceed confidently to writing and compiling your first pieces of code. Now let's see how we can implement a simple Hello World program in Zig. First, we start by importing the standard library which provides essential functionality for our program. The pub-fn main line defines the main function, serving as the entry point. The void indicates that this function may return an error, which aligns with Zig's robust error handling capabilities. Next, we create a variable stdout that will provide a writer for standard output. This is achieved by calling std get stdout writer, which allows us to easily send output to the console. The use of try in front of stdout print is significant. It ensures that if the print operation encounters an error, it will propagate that error up, maintaining clear error management. Finally, we call stdout print with the message hello world, followed by a newline character. This displays the text to the console when we run our program. To execute the code, you can use the terminal command zig run hello.zig, and upon successful execution, you will see your greeting on the screen. This straightforward program exemplifies the clean, user-friendly syntax of Zig while demonstrating key features like error handling and standard output. Now let's see how we can declare and initialize variables in Zig, a fundamental aspect of programming that allows us to store and manipulate data. First, we can create a variable named number that holds a 32-bit integer by specifying its type explicitly. This clarity in type declaration is important for type safety, ensuring that the correct data types are used throughout our program. Next, we will see how Zig supports type inference, allowing us to initialize a variable without explicitly declaring its type. In this case, we can create a variable named name and assign it the string value Zig. The compiler will automatically infer that name is of type string based on the assigned value. This feature streamlines our code, making it more concise without sacrificing clarity. Through these examples, you can see how Zig promotes both explicit type declaration for safety and type inference for simplicity, creating a balance that aids in writing clean and effective code. Now let's see how we can define and use functions in Zig. The function we will be implementing is called add, which takes two parameters, x and y, both of type i32, representing 32-bit integers. This function's purpose is to return the sum of these two numbers, also as an i32. Here you can notice that Zig requires us to specify the types of both the parameters and the return value, which helps enhance the type safety of our program. Type safety is particularly useful in larger code bases, as it reduces the risk of type-related errors. Next, we will call this function by passing the integers 5 and 10. The result of this operation will be assigned to a constant variable named result. After executing the code, result will hold the value 15, confirming that our function works correctly. This simple yet powerful function demonstrates how Zig encourages clarity and strong typing in function definitions, making it easier for developers to read and maintain code. Next, we will write a function called safeDivide that demonstrates Zig's error handling capabilities. This function takes two integers as parameters, x and y, and is designed to perform a division operation. However, to ensure safety, it checks if the divisor y is 0. If y is indeed 0, the function does not proceed with the division. Instead, it returns a specific error variant, error, division by 0. This approach prevents runtime crashes due to division by 0 and reinforces the importance of handling potential failures proactively. Now let's see how we can utilize this function with Zig's try statement, which simplifies error handling when calling functions that may fail. In our example, we call safeDivide with the values 10 and 2 and use try to manage the function's outcome. If the division operation is successful, the result will be stored in the variable result. However, if it encounters an error, the error will be directly returned without requiring extra error-checking code. This not only reduces boilerplate, but also leads to a cleaner, more maintainable code structure, allowing developers to focus on the core logic. Now let's see how we can implement memory management in Zig using the manual allocation approach. In the code, we start by importing the standard library, which gives us access to various built-in functions and types. The main function is defined with the potential to return an error, signified by the void return type, which is common in Zig to handle expected failures elegantly. We initialize the memory allocator using the std heap page allocator, allowing us to allocate memory dynamically. Then we use the allocator alloc method to request memory for an array of 10 integers. Here, the try keyword is crucial as it captures any errors that may occur during allocation, promoting robust error handling practices. Next, we utilize the defer statement to ensure that the allocated memory is properly freed when the function scope is exited, mitigating the risk of memory leaks. Within the allocated memory, we populate the array with values by multiplying each index by 10, demonstrating how to modify dynamic memory. Finally, we output the values of the array to the console, showcasing both the dynamic memory allocation and the safe handling of resources in Zig, which intertwines performance with safety. Now let's implement a basic asynchronous function in Zig that simulates a delay. This function, defined as delay, takes an unsigned integer parameter representing the number of seconds to wait. Inside the function, we first calculate the time in nanoseconds using a constant from Zig's standard library, which gives us the number of nanoseconds per second. We then use the try keyword along with std time sleep to pause execution for the specified duration. This method allows us to enforce error handling, as the function may return an error if the sleep operation fails. Next, we will write the main function to call our delay function. We declare a constant delayed task that stores the result of calling delay 2, which means we are simulating a 2-second delay. The comment in the code suggests that while this task is running, other operations can be performed concurrently. Finally, we use try again to ensure that we handle any potential errors when we invoke delayed task. This illustrates how Zig's concurrency model allows us to execute tasks without getting bogged down by traditional threading complexities, promoting clarity and safety in handling concurrent operations. Now let's take a look at how to set up a Zig project using a build.zig file. This file is crucial as it defines the configuration needed for building your application. Here, we start by importing the builder from the standard library, which provides the functionality for setting up builds. Next, we define a public function named build that takes a pointer to a builder instance. Within this function, we create an executable target using the addExecutable method, specifying both the name of the executable and the path to the main source file of our application, which in this case is located in the src directory. We then set the target architecture to x86-64 for Linux systems and select a build mode that optimizes for speed with release fast. This configuration is particularly beneficial as it enables the application to run efficiently in a production environment. Finally, the install artifact function is called to ensure that the built executable is properly installed in the desired location. This seamless organization allows you to easily manage your project's dependencies and build settings, which is especially important as your codebase grows. So far, we've covered a breadth of topics that introduce Zig, including installation, syntax, functions, error handling, memory management, concurrency, and modularity. We've seen how Zig allows for both manual control and safety, making it especially appealing for systems programming. In the upcoming lessons, we will further investigate advanced topics, particularly around concurrency and memory management. Zig's unique features make it a powerful choice, and I hope you feel equipped to start exploring and creating with this language. Zig is not just a language, it's a toolkit that empowers developers to write safe and efficient programs. As you practice and explore more, you'll find that the experiences you create will be robust and enjoyable. Happy coding with. Now let's see how we can calculate the sum of the first 100 integers using Zig. In this example, we begin by declaring a variable sum of type i32 and initializing it to 0 to hold our total. Next, we use a for loop which iterates over the range from 1 to 100. This is done using the range syntax i32 1 equals 100, which allows us to include both endpoints. Within the loop, we add each integer I to the sum variable. This succinct accumulation showcases how straightforward operations can be executed in Zig. After completing the loop, we utilize std debug print to output the result to the console, demonstrating how easy it is to handle formatted output in Zig. The use of curly braces within the print function indicates where our sum variable will be inserted into the output string. This simple yet effective piece of code illustrates not only the performance of Zig through its efficient compiling and execution, but also its clear syntax, allowing developers to focus on the logic without unnecessary complexity. Now let's see how we can implement dynamic memory allocation in Zig. In this example, we begin by importing the standard library, which provides essential functionalities like memory allocation. Next, we define the main function, which is the entry point of our program. Here, we create an allocator using the page allocator, which facilitates the allocation of memory on the heap. We then dynamically allocate memory for an array capable of holding 5 integers. It's important to note the use of try, which will handle any potential errors during allocation. If the allocation is successful, we proceed to populate the array with values that are double their index, showcasing how we can manipulate the data within the allocated space. To ensure that we prevent memory leaks, we utilize the defer statement to schedule the memory release, guaranteeing that it will be freed automatically when the function exits. Finally, we loop through the array to print out each value, demonstrating both data manipulation and safe memory management. This example illustrates not only dynamic memory allocation, but also the importance of proper memory handling in Zig. Now let's see how we can implement a safe division function in Zig that handles errors gracefully. In this example, we define a function called safe_divide, which takes 2 integer parameters, the numerator and the denominator. The function begins by checking if the denominator is 0, which would lead to an undefined operation. If it is, the function returns a specific error indicating a division by 0, utilizing Zig's first-class error handling feature that allows us to return errors directly as types. This explicit error handling simplifies the management of potential issues, making our code easier to read and maintain. Following this, we implement the main function, where we attempt to call the safe divide function with the values 10 and 0. By using the try keyword, we encapsulate the call in a way that automatically propagates any errors that may occur, ensuring we gracefully handle the error without crashing the application. If a valid result is returned, we can then print it out, showcasing the clean and efficient error management capabilities Zig provides. Now let's explore how to create an executable for a specific target platform using the build configuration in Zig. We start by importing the necessary build module, which gives us access to the builder functionality required for our build script. Next, we define a function named build that takes a pointer to a builder instance as its parameter. Inside this function, we proceed to add an executable to our build process, naming it myapp and linking it to the source file located in src/main.zig. This process specifies the entry point of our application. After defining the executable, we set its target to target x86-64 Linux, indicating that we want our application to be compiled for a 64-bit Linux environment. Furthermore, we choose a release build mode optimized for speed with build mode release fast. Finally, we execute b install artifact exe, which takes care of installing the built executable in the appropriate location. This streamlined process allows you to focus on coding, knowing that Zig's build system manages the intricacies of cross-compilation for different operating systems effortlessly. Next, we will look at how to define a data structure in Zig, specifically a point structure, which encapsulates the coordinates and provides a method to calculate the distance from the origin. In this code, the point structure is defined with two fields, x and y, both of type f64, allowing for floating point values. This clear definition not only organizes the data, but also makes it easier to understand how different values relate to one another. Now let's implement a method called distance, which computes the distance from the origin using the mathematical formula for Euclidean distance. This method uses the std.math sqrt function to calculate the square root of the sum of the squares of the coordinates. In the main function, we create an instance of point named pointa and initialize it with specific values. We then call the distance method on this instance to compute the distance. Finally, we output the result using the std.debug print function, which provides a clean and straightforward way to display the distance calculated. This example illustrates not just the functionality, but also the clarity and conciseness of Zig's syntax, enhancing readability and maintainability. Now let's see how we can implement an async function in Zig to handle concurrent tasks effectively. The fetchData function is defined with the async keyword, indicating that it will run asynchronously. Inside this function, we simulate a network call by using std time sleep 20000000000, which pauses execution for 2 seconds. This simulates the time it might take to fetch data from an external source. The key advantage here is that while this function is waiting, the main thread is free to perform other operations, which enhances the overall efficiency of the program. In the main function, we initiate the fetchData call and store the resulting task in a variable. This allows us to keep track of it while potentially executing other code in the main thread. After initiating the fetch, we invoke tryTask to await the completion of the fetch operation and handle any errors that might occur during execution. The use of async and await in Zig simplifies writing concurrent code, enabling developers to build responsive applications without the complexity often associated with traditional threading models. This demonstrates Zig's capability in enhancing performance and developer productivity through its efficient concurrency model. Next, we will write a simple project layout to demonstrate the modularity of Zig, which is essential for maintaining a clean structure in larger applications. The layout consists of a main directory containing a build.zig file along with a src folder. This src folder holds individual modules, such as main.zig, module1.zig, and module2.zig. By organizing functionality into separate modules, we improve code clarity and enhance reusability. Each module can encapsulate specific features or functionalities, allowing developers to focus on smaller, manageable parts of the application without getting lost in monolithic code files. For instance, main.zig could serve as the entry point, while module1.zig and module2.zig could contain distinct functionalities relevant to the application. This structure not only encourages better collaboration among team members, but also simplifies the process of maintaining and evolving the application over time. When changes are needed, they can be isolated to specific modules, reducing the risk of unintended side effects. Overall, this modular approach exemplifies how Zig's project organization capabilities contribute to improved development practices. In conclusion, Zig is an innovative programming language that boasts an impressive set of features, including performance optimization, manual memory management, clear error handling, cross-platform capabilities, simplicity in syntax, robust concurrency handling, and smart modularity. As you continue your journey with Zig, these aspects will become the building blocks for crafting efficient, safe, and maintainable applications. Zig is more than just a programming language. It's a toolkit designed with the developer's experience in mind. As we delve deeper into upcoming lessons, we'll explore advanced topics that will further enhance our understanding of what Zig has to offer and empower you to leverage these features effectively in your projects. Happy coding! Zig is a general-purpose programming language designed with a focus on performance, safety, and developer productivity. If you're looking for a modern alternative to traditional languages like C and C++, you've come to the right place. In this lesson, we'll explore the essence of Zig and how its unique features set it apart from other programming languages. So far, we learned that Zig emphasizes performance, safety, and developer productivity, with features like manual memory management and robust error handling. We explored the installation process, basic syntax, and concurrency model, along with how Zig optimizes performance through its compiled nature. Additionally, we discussed how Zig simplifies cross-platform development, promotes clear and maintainable code, and enhances modularity for better project organization. Now we will cover Zig's essential features, its syntax, and why it's a great choice for various applications. Zig was created by Andrew Kelly, who was inspired by the need for a language that was both performant and simple to use. You might be wondering what's so great about Zig. Well, the language is designed to provide developers with high performance without sacrificing safety or productivity. This makes it an attractive option for system-level programming, game development, and more. Let's begin by diving into the core features of Zig. One of the most significant features is its *** focus on performance ***. Zig compiles to native code, which means that your programs will run almost as fast as those written in C. This is critical for applications that need optimal speed, such as game engines or performance-critical systems. Now let's see how we can implement a simple program in Zig that calculates the sum of two numbers. First, we start by importing Zig's standard library, which provides essential functionality for debugging and input-output operations. In the main function, we declare two integer constants, x and y, initialized with the values 5 and 10, respectively. These variables represent the numbers we will be adding. Next, we define a helper function called add, which takes two integer parameters, a and b, and returns their sum. This demonstrates Zig's clean syntax and the ability to create reusable functions. By calling add x, y, we compute the sum of x and y, storing the result in another constant called sum. Finally, we use the std debug print function to display a formatted message on the console that shows the values of x, y, and their sum. This not only showcases basic arithmetic operations, but also highlights Zig's emphasis on clear and efficient code that's easy to read and maintain. Now let's see how we can implement manual memory allocation in Zig, emphasizing its safety features. In this example, we start by importing the standard library, which provides essential functionalities that we will utilize. Next, we define the main function where we first set up the allocator by using Zig's built-in page allocator. This allocator allows us to request a specific amount of memory dynamically. Following this, we allocate memory for an array of 5 integers while employing the try keyword, enabling automatic error handling during the allocation process. Should the allocation fail, the try will propagate the error, aligning with Zig's robust error handling philosophy. After successfully obtaining our memory, we proceed to populate the array with values, filling it with even numbers through a simple loop. To demonstrate the stored values, we utilize std debug print, which outputs each element alongside its index to the console. This not only reinforces our understanding of memory management, but also highlights the safety of Zig as we handle the memory carefully. Finally, we free the allocated array, ensuring we avoid memory leaks and maintain control over resource management. This example illustrates the hands-on approach Zig takes towards memory safety and developer responsibility. Now let's take a look at how to set up a simple Zig build file using the integrated build system. In this code, we first import the standard library, which provides essential functionalities for our program. The main feature here is the build function, which takes a pointer to a build builder as its argument. This builder is crucial for managing the build process. Next, we create an executable named hello by calling the addExecutable method, specifying the name and the path to the source file. This makes it easy to specify the target application. Subsequently, we use setTarget and setBuildMode methods to configure the executable according to the parameters passed during the build, allowing for flexibility in different environments or needs. Finally, the install method is called to ensure that the executable is correctly installed, making it ready for use. This simple setup demonstrates Zig's goal of keeping the build process minimal and efficient, significantly enhancing developer productivity by automating repetitive tasks that are often cumbersome in other languages. Now let's take a look at how we can utilize Zig's modularity feature by creating and importing modules. First, we define a separate file called utils.zig, where we implement a simple function, add, that takes two integers as parameters and returns their sum. This separation allows for better organization of code, making it reusable across different projects or parts of the same project. Next, in our main program, we import the standard library as well as our utils.zig module. By using the @import directive, we can access the functionality defined in our utility module. In the main function, we call the add function from the utils module, passing in the numbers 3 and 4. The resulting sum is stored in the result variable and then printed to the console with a clear message. This example not only showcases the ease of creating and utilizing modules in Zig, but also illustrates how modularity contributes to maintaining and scaling applications effectively as they advance. Now let's see how we can implement concurrency in Zig. In this code snippet, we begin by defining a function named task, which, when executed, simply prints a message indicating that it is running. This encapsulation of behavior is foundational in concurrent programming, as it allows us to define the work we want to execute in parallel. Next, within the main function, we utilize Zig's threading capabilities by spawning a new thread to run the task function concurrently. The thread is created using std thread spawn, which allows us to generate a separate execution path without blocking the main program flow. This approach is crucial for enhancing application responsiveness and performance, especially in multi-core environments. After spawning the thread, we immediately call threadWait, which ensures that the main program will pause execution until the spawned thread has completed its task. This synchronization is vital to prevent premature termination of the main function and ensures that all tasks are appropriately handled before exiting the program. This simple yet effective use of threads exemplifies Zig's ease of use in concurrent programming and its suitability for high-performance applications. Now let's explore how Zig seamlessly interfaces with C code by integrating a simple C function. We'll begin with a C file where we define a function named hello that prints a welcoming message to the console using the standard print function. This function serves as a straightforward example of how existing C functions can be incorporated into a Zig project. Next, we will write the corresponding Zig code to utilize this C function. In the Zig file, we start by importing the standard library, which provides essential functionalities for our program. We then declare an external function, hello, specifying that it's defined in C. This step is crucial as it prepares Zig to recognize and link to the C function at compile time. Now let's implement the main function in Zig. Inside this function, we call the hello function that we declared earlier. When the Zig program runs, it will execute the hello function defined in C, allowing us to see the output from the C code directly in our Zig application. This interoperability highlights Zig's capability to leverage existing C libraries while benefiting from its modern features, fostering efficient development practices. In conclusion, we've covered a lot today, from Zig's focus on performance, safety, and developer productivity to its modular approach and robust concurrency model. Zig is not just a programming language, it's a tool that empowers developers to build efficient and safe applications while enhancing productivity. As we move forward, we will explore more advanced concepts and begin tackling real-world problems using Zig. Get ready to dive deeper into the fascinating world of Zig programming as we uncover its advanced functionalities and best practices. Now let's take a look at an example implementation of a recursive function to calculate the factorial of a number, showcasing the performance capabilities of Zig. We begin by defining a function named factorial that takes a 32-bit unsigned integer as input. The function uses a simple conditional statement to check if the input number is 0. If it is, it returns 1, as the factorial of 0 is defined as such. For other values, the function recursively calls itself, multiplying the current number by the factorial of the number decreased by 1, efficiently calculating the factorial through recursion. Next, we introduce the main function, which serves as the entry point of the program. Here we declare a constant number and set it to 5, intending to calculate the factorial of this number. We then invoke our previously defined factorial function with number as an argument and store the result in a constant named result. To output the result, we use std debug print, which effectively illustrates Zig's straightforward syntax by formatting and displaying the calculated factorial. This implementation not only highlights the recursive nature of the function, but also demonstrates Zig's performance optimizations during compilation, making it a suitable choice for performance-critical tasks. Now let's see how we can implement dynamic memory allocation in Zig to emphasize safety in memory management. In this example, we begin by importing the standard library, which gives us access to the memory allocation features. The main function is declared to return a result type, allowing for proper error handling. We then define a page allocator, which is a built-in allocator suitable for our use case. Next, we'll allocate an array of 5 32-bit unsigned integers using the alloc method of the allocator. By wrapping this action in a try expression, we can gracefully handle any potential errors that may arise during memory allocation. After successfully obtaining our memory, we iterate through the array to assign values, demonstrating how to both populate and access array elements effectively. Each element is assigned a value derived from its index, showcasing the ease of manipulation within memory. Lastly, to promote good memory hygiene and avoid leaks, we must free the allocated memory using the allocator free function once our operations are complete. This attention to memory management design is what reinforces Zig's commitment to safety and reliability for developers. Now let's see how we can implement a simple build file in Zig to streamline project configuration. This build file defines an executable named hello, which is linked to the source file located at src/main.zig. By utilizing the setTarget function, we can specify the compilation target for our application, ensuring it runs optimally across different environments tailored to the desired architecture. Similarly, setBuildMode allows us to adjust compilation settings, whether we need a debug or release build, which can be critical for performance and debugging. Moreover, the install function neatly encapsulates the installation process, making it straightforward to deploy our executable after building. With this structure, Zig's integrated build system significantly reduces setup complexity, allowing developers to focus more on writing code rather than managing the build process. This concise approach not only enhances productivity, but also supports maintaining consistency across builds, crucial when working in collaborative or multi-environment settings. As we continue, this focus on developer-friendly features will help us appreciate how Zig caters to modern programming needs. Now let's implement a utility module for mathematical operations that enhances code reusability. We'll start by defining two public functions, add and subtract, in a separate file named math.zig. The add function accepts two integers as parameters and returns their sum, while the subtract function performs a similar role by taking two integers and returning the result of subtracting the second from the first. By encapsulating these functionalities within a dedicated module, we maintain a clean structure that separates our mathematical logic from the main application. Next, we will see how we can use this module in our main application. We will import math.zig at the beginning of our code, which allows us to access the add and subtract functions directly. In the main function, we will call both functions with sample values 10 and 5, storing the results in variables named sum and difference. Finally, we'll output the results using std debug print, showcasing how easy it is to utilize modular functions without cluttering our main logic. This approach not only simplifies our code, but also encourages maintainability, making it easier for teams to collaborate effectively. Now let's see how we can implement concurrency in Zig through a straightforward example. The process data function acts as a simulated workload where it takes an integer input and prints a message indicating that the data is being processed. This function exemplifies a task that can run independently of other tasks. Next, in the main function, we create two threads using std thread spawn, which allows us to initiate these concurrent tasks. Each thread runs the process data function with a different argument, demonstrating how we can handle multiple operations simultaneously. The values 1 and 2 are passed to the threads to simulate parallel processing of different data sets. To ensure that the main program waits for both threads to complete their operations before proceeding, we call the wait method on each thread. This feature highlights Zig's built-in support for concurrency, making it easy to manage multiple tasks without intricate complexity. By utilizing this approach, developers can effectively utilize system resources, boosting performance for applications that require simultaneous task execution, such as web servers or simulation engines. Now let's see how we can call a simple C function from within Zig to illustrate its interoperability with existing C code. First, we begin with a C implementation where we define a function named greet. This function utilizes the standard input-output library to print the message "Greetings from C" to the console. This demonstrates how straightforward it is to create a basic function in C. Next, we implement this function in Zig by declaring it as extend C fn greet. This declaration allows Zig to recognize and link to the C function seamlessly. Then in the main function, we simply call greet. This single call showcases the ease with which you can integrate C functionality into a Zig application. Such interoperability is powerful, as it allows developers to incorporate existing C libraries, resulting in faster development cycles without the need to duplicate functionality. Overall, this example clearly demonstrates how Zig's design facilitates the blending of both languages, providing developers with great flexibility in their projects. In conclusion, today we unpacked quite a bit, covering the rich features and benefits of Zig. We talked about performance through native code compilation, emphasized safety with explicit memory management, and explored how developer productivity is enhanced with an integrated build system and modularity. We examined concurrency to handle simultaneous tasks and highlighted the language's compatibility with C for pragmatic coding solutions. Zig is designed to be efficient and accessible, whether you are building performance-sensitive applications or integrating systems seamlessly. We've only just scratched the surface, and Zig has so much more to offer. Keep exploring, and let's dive deeper into advanced concepts and practical applications in our upcoming Zig is a general-purpose programming language designed with a focus on performance, safety, and developer productivity. It holds the promise of becoming a robust alternative to languages like C and C++. In this tutorial, we'll explore Zig's unique core features, its syntax, and how it differentiates itself from other programming languages. So far, we learned that Zig is a high-performance programming language focused on safety and developer productivity. Serving as a viable alternative to C, we explored its core features like manual memory management, robust error handling, and a streamlined build system that enhances coding efficiency. Additionally, we discussed Zig's modular approach for code organization, built-in concurrency support for managing simultaneous tasks, and its seamless interoperability with C. Overall, Zig presents a wealth of capabilities for building efficient and safe applications, paving the way for further exploration in future lessons. Now let's take a look at a simple program that computes the Fibonacci series in Zig. We start by defining a recursive function called Fibonacci, which takes an unsigned 32-bit integer n as input. This function implements the classic Fibonacci algorithm, returning the value of n if it is less than or equal to 1 as the base cases of the series. For any other value of n, it recursively calls itself, adding the results of Fibonacci n1 and Fibonacci n2. In the main function, we set up a loop that iterates from 0 to 9, representing the first 10 Fibonacci numbers. During each iteration, we call the Fibonacci function and utilize Zig's built-in standard library to print the index along with the corresponding Fibonacci number to the standard debug output. This example demonstrates how Zig's performance and efficiency allow the program to execute quickly, even with recursion, showcasing its capability to handle algorithmic computations effectively. Understanding such fundamental constructs is crucial as they lay the groundwork for building more complex applications in Zig. Now let's take a look at a simple example of managing arrays safely in Zig. In this code, we declare a fixed-size array containing 5 unsigned integers initialized with values from 1 to 5. This approach highlights Zig's emphasis on safety by ensuring that the array's size is determined at compile time, reducing runtime errors. Within the main function, we use a for loop to iterate over the array's indices from 0 to its length. During each iteration, we make use of Zig's debugging facilities to print out each element alongside its index. The beauty of Zig's safety features is exemplified here. If we attempt to access an index that lies outside the boundaries of the array, Zig will either produce a compile time error or a runtime panic. This strict boundary checking helps prevent common pitfalls experienced in other languages, such as buffer overflows, ensuring that our program runs reliably. This pattern of utilizing fixed size arrays and safe index accesses is a fundamental aspect of writing secure and efficient code in Zig. Now let's take a look at how we can define a basic structure in Zig by creating a point struct that exemplifies the language's clean and straightforward syntax. In this code, we define the point structure with two properties, x and y, which represent the coordinates of a point in a two-dimensional space. Additionally, we implement a method called distanceDa that calculates the distance between two point instances. This method takes a pointer to another point as a parameter and returns the computed distance as a floating point number. The distance is calculated using the Euclidean distance formula, which involves basic arithmetic operations and the square root function from Zig's standard library. Next, we create two instances of point, P1 and P2, initializing them with specific coordinates. We then use the std debug print function to display the result of invoking the distanceDa method on P1, passing P2 as the argument. This concise implementation illustrates how Zig's syntax encourages clarity and productivity, allowing developers to focus on functionality without unnecessary complexities. Now let's take a look at how we can implement modularity in Zig with a simple example. We will create a module named mathutils that encapsulates the functionality of adding two integers. In this module, we define a public function called add, which takes two parameters, a and b, both of type i32. This function performs the addition of these two integers and returns the result. Next, we will see how we can use this mathutils module within our main program. We start by importing the standard library in our mathutils module. Within the main function, we call the add function from mathutils, providing it with the values 5 and 3 as arguments. The result of this addition is stored in a constant called result. Finally, we utilize the std debug print function to output the result to the console, displaying the sum. This approach of using modules not only improves code organization by keeping related functionality together, but also enhances code reusability, making maintenance easier and allowing different parts of the application to be developed in isolation. Now let's see how we can implement concurrency in Zig using threads. In our example, we begin by defining the main function and specifying the number of tasks we want to run concurrently with const num tasks, u32 equals 5. We then declare an array of threads to hold the tasks we'll be creating. Next, we enter a loop where we spawn multiple threads using std thread spawn. For each task, we define an asynchronous block that contains the logic for the task, in this case, printing a message indicating that the task is running. The use of the asynchronous block allows Zig to manage the underlying complexity of thread handling, letting developers focus on what each task needs to accomplish without getting bogged down in low-level thread management. After spawning all the threads, we proceed to another loop where we call join on each thread. This is an essential step because it ensures that the main program waits for all the tasks to complete before exiting. Through this implementation, Zig provides a clean and efficient way to execute parallel tasks, showcasing its powerful concurrency features that enhance developer productivity while ensuring performance. Now let's see how we can leverage C code within our Zig applications, showcasing the language's strong interoperability features. In this example, we begin with a simple C library, where we define a function named hello from C. This function, when called, prints a message to the console indicating that it's coming from C. Next, we will write the Zig code that allows us to access this C function seamlessly. We use the @c_import directive to include our C library, ensuring that Zig recognizes the function we intend to use. Within the main function of our Zig program, we call C hello from C, which triggers the execution of the C function we imported. This direct integration demonstrates how easily Zig can interact with existing C codebases, allowing developers to reuse libraries and functions without rewriting them in Zig. Such flexibility not only speeds up development, but also supports the transition of legacy systems into more modern architectures, marrying performance with practical reusability. This interoperability is a significant asset for developers looking to combine the strengths of both languages effectively. As we wrap up this introduction to Zig, remember that we've just scratched the surface. We've covered critical aspects like performance, safety, developer productivity, modular design, concurrency, and interoperability. Zig's modern design philosophy aims to make a balance between being fast, secure, and easy to use. In future lessons, we will dive deeper into specific concepts like error handling, build systems, and advanced language features that Zig has to offer. Zig gives developers powerful tools to build safe and efficient applications with a strong focus on their productivity. So whether you are looking to optimize system-level code or develop applications where performance matters, Zig has something to offer. Stay tuned as we explore more in the upcoming lessons because, with Zig, the possibilities are as broad as your imagination. Now let's take a look at how we can utilize manual memory management in Zig. In our example, we begin by importing the standard library, which provides access to essential functionalities. We define the main function where we create an instance of the page allocator, a built-in memory management tool in Zig that allows us to allocate blocks of memory efficiently. Next, we allocate a buffer of 1024 bytes using the allocator alloc function, specifying the type of data we intend to store as U8, which represents an unsigned 8-bit integer. This allocation process is wrapped in a try expression, allowing us to handle any potential errors that might arise during memory allocation, maintaining the robustness of our application. To ensure that we manage memory correctly and prevent leaks, we use the defer keyword, which schedules the release of the allocated memory back to the allocator once it goes out of scope. This feature not only simplifies memory management, but also enhances program safety by reducing the possibility of memory leaks. This example demonstrates how Zig's manual memory management capabilities empower developers to take control of resource allocation while prioritizing performance and safety in their applications. Next, we will write a piece of code that demonstrates Zig's approach to error handling using custom error types. In this example, we define a custom error called myError with a specific variant, value too high, which allows us to communicate clear and intentional error conditions. The function compute takes an unsigned integer input and can either return a successful result or an error, indicated by the before the return type. Within the function, we check if the input value exceeds a predefined threshold of 10. If it does, we return the custom error, value too high, effectively signaling that the input is not valid for this operation. Now let's take a look at how we handle the result of this computation in the main function. Here, we invoke the compute function with a value that triggers the error condition. By utilizing a switch statement, we can clearly differentiate between a successful computation and an error. When the result is an error from myError, we print an informative message about the issue. This structured error handling pattern not only improves code readability, but also enhances robustness by ensuring developers can manage error conditions explicitly and gracefully. Now let's see how we can implement a compile-time computation of the factorial of a number using Zig. In this example, we define a function called factorial that takes an unsigned 32-bit integer, n, as an argument. The function employs recursion to calculate the factorial. When n equals 0, it returns 1, as the factorial of 0 is defined as 1. Otherwise, it multiplies n by the factorial of n1, effectively building up the factorial value through recursive calls. Then in the main function, we call the factorial function with the value 5. Since Zig has the capability of evaluating this function at compile time, it computes the factorial of 5 before the program even runs. This means that when we execute the program, it retrieves the pre-computed result immediately, eliminating any computational overhead during runtime. The std debug print function is then used to display the calculated factorial in the output. This showcases Zig's powerful feature of compile-time execution, which enhances performance and reliability by optimizing code before it is executed. Now let's see how we can implement a separate module for mathematical utilities in Zig to enhance code organization and maintainability. We begin with the creation of a file named mathutils, Zig, where we define two fundamental functions, add and multiply. The add function takes two integers as parameters, sums them, and returns the result, while the multiply function performs a similar operation for multiplication. This encapsulation of mathematical operations within a dedicated module allows us to keep our codebase organized, promoting reuse and ease of modification. Next, we integrate these functions into our main application file. This is achieved by importing our mathutils module, which brings in the functionality needed for our application. Within the main function, we call the add and multiply methods, passing in values to compute the sum and the product of 3 and 4, respectively. Finally, we print the results using std debug print. This approach, utilizing modular design, not only clarifies the implementation by segmenting functionality, but also empowers developers to work collaboratively on different features without overlapping code changes. Now let's take a look at how Zig implements concurrency through the use of threads. In this example, we first define an array to hold 5 threads using Zig's std thread type. The for loop initializes these threads by spawning concurrent tasks that will run simultaneously. Each task executes an asynchronous block where a message is printed to indicate which specific task is currently executing. This illustrates Zig's ability to handle concurrent programming with minimal complexity, allowing you to focus on the core logic rather than intricacies like thread management. Once all threads are spawned, we have another for loop where we call the join method on each thread. This ensures that the main program waits for all tasks to complete before proceeding, effectively synchronizing their execution. Zig simplifies multi-threaded programming, letting developers efficiently launch and coordinate tasks without the usual worries about race conditions and deadlocks, thus enhancing application responsiveness and performance. This example exemplifies how Zig's built-in support for concurrency can facilitate high-performance applications capable of executing multiple operations simultaneously. Now let's implement a simple interaction between Zig and C, showcasing how we can call a C function from our Zig code. First, we need to create a C source file named clibc, where we define a function called greet. This function uses the standard I/O library to print a message to the console, demonstrating how C functions can be utilized in Zig programs. Next, we move to our Zig code, where we begin by importing the standard library for necessary functionality. Then we utilize Zig's @c_import directive, which plays a critical role in including C code into our Zig program. Inside the c_import, we specify the inclusion of our clibc file, allowing us to access the greet function. In the main function of our Zig code, we simply call cgreet. This line effectively translates to executing the C function greet, resulting in the message from the C library being printed. This seamless integration exemplifies the interoperability of Zig with C, allowing developers to leverage existing C functionalities effortlessly and facilitating a smooth transition for projects moving from C to Zig without sacrificing any essential capabilities. As we wrap up our exploration of Zig's features, it's evident that this language is finely tuned for the modern developer. With its emphasis on manual memory management, strong error handling, compile-time execution, modular design, built-in concurrency, and seamless C interoperability, Zig presents a comprehensive suite of tools that all contribute to increasing developer efficiency and safety in application development. In summary, Zig is not just another programming language. It's a powerful ally for developers committed to writing high-performance, reliable, and efficient code. The methodologies Zig employs aim to enhance productivity, making it a compelling choice for developers looking to innovate and optimize in a rapidly evolving technological landscape. The potential Zig holds can be unlocked further as we delve deeper into specific advanced topics in the upcoming lessons. So brace yourselves, Zig is just getting started. Zig is a general-purpose programming language designed with a focus on performance, safety, and developer productivity. In a world where programming languages evolve rapidly, Zig stands out by offering a blend of features that make it ideal for modern software development. Today's lesson will delve into the essentials of Zig, helping you understand its core principles and practical applications. So far, we learned that Zig is a high-performance programming language emphasizing safety and productivity. With features such as manual memory management, robust error handling, and seamless interoperability with C, we explored how Zig's modular design promotes organized code and reusability, as well as its support for concurrency, simplifying multi-threaded application development. Additionally, we discussed the significance of compile-time code execution for performance optimization. Overall, Zig equips developers with powerful tools aimed at enhancing efficiency while building safe and robust applications. Now, we will talk more in depth about Zig's fundamental features and how to get started using them effectively. Now let's see how we can implement a basic Hello World application in Zig. The program begins by importing the standard library with import std, which provides essential functions and types that facilitate various operations within the language. The main function serves as the entry point of the program where the execution begins. Inside this function, we utilize std debug print to output the string hello world to the console. The escape sequence \n is included to add a new line after the printed message, ensuring a clean output. Upon running this code, users will see hello world displayed in their console, confirming that their Zig installation is set up correctly and functioning as expected. This simple example captures the essence of a Zig program and highlights the language's straightforward syntax and ease of use. laying the groundwork for more complex applications as we delve deeper into Zig's features in future lessons. Now let's see how we can manage memory allocation in Zig using a manual approach. In the following example, we start by importing the standard library, which gives us access to the essential functionalities needed for memory management. We declare a variable named allocator, which we initialize with std heap page allocator. This allocator allows us to dynamically allocate memory in our program. Next, we'll allocate an array of 100 bytes using the alloc method of our allocator. It's important to handle potential memory allocation failures gracefully, thus we utilize a catch clause. This ensures that if an error occurs during memory allocation, we log a meaningful message to the console instead of allowing the program to crash. Once we successfully allocate the memory, we can utilize it, for instance, by filling the array with values ranging from 0 to 99. Finally, after we are done using the allocated memory, we must explicitly free it using the free method of the allocator. This step is crucial in Zig to prevent memory leaks, highlighting the language's commitment to safety and efficient resource management. By implementing this pattern, we gain both control and responsibility over memory in our Zig applications. Next, we will write a simple program that demonstrates how to check if a number is odd or even using a conditional statement in Zig. In this example, we define a constant integer variable, number, and assign it a value of 5. We then use the modulo operator % to determine if the number is divisible by 2. If the condition evaluates to true, meaning the number is even, the program prints the message indicating that it is even. Conversely, if the number is odd, the alternative branch executes and it prints that the number is odd. This straightforward syntax flows naturally, enhancing readability and ease of use, which is one of the key design philosophies of Zig. The program effectively utilizes Zig's debugging capabilities through the std debug print function, providing clear output to the console. This structure not only illustrates how to handle basic conditions, but also reinforces the language's emphasis on clarity and simplicity, making it an excellent learning example for newcomers. Now let's take a look at how we can implement a basic math module in Zig. In this example, we define a function called square, which takes a floating point number as input and returns its square by multiplying the number by itself. By using the export keyword, we make this function accessible to other modules, which is essential for reusing code across different parts of an application. Next, we set up our main file, where we import the standard library and our newly created math module. We use the @import directive to bring in the math module, allowing us to access its functionality. Inside the main function, we call mathSquare with the value 5, 0, which triggers the execution of the square function we defined earlier. The result is stored in the variable result. Finally, we utilize std debug print to output the computed square of the number. This example demonstrates how Zig's modularity promotes clean and organized code, making it easier to maintain and reuse components across larger projects. Now let's take a look at a simple example that showcases how to use channels for communication between goroutines in Zig. In this code, we start by importing the standard library and defining the main function, where we initialize a memory allocator. We then create a channel capable of transmitting integers, specifying a capacity of 10. This channel acts as a thread-safe communication medium between the main function and a worker goroutine. Next, we spawn a new goroutine named worker, which will execute the worker function, passing the channel as an argument. This means that our program can continue executing while the worker is processing its tasks. Following this, we send the integer value 42 through the channel, which represents data being transferred to the worker. To demonstrate the effectiveness of this setup, the main function then receives a value from the channel, which is the value previously sent. Finally, we print out the received value in the main function, which showcases how data can be efficiently shared between concurrent tasks. This pattern simplifies task coordination in multi-threaded applications, making it essential for achieving high performance in Zig. Now let's see how we can set up a build configuration in Zig to target different operating systems efficiently. In this code, we start by importing the standard library's build module, which provides necessary tools for the build process. The build function then takes a pointer to a builder, which is responsible for managing the build settings. Inside the function, we detect the target operating system using btarget, which allows us to adapt our build process based on the environment it runs in. We then create an executable file named myapp sourced from the src/main.zig file. This step is crucial as it prepares our program for execution on the specified target OS. By calling exec set target, we ensure that the executable is compiled for the detected operating system without any manual adjustments to the codebase. Finally, the call to exe install facilitates seamless deployment of the compiled executable, making it easy for developers to manage their applications across various platforms. This structure not only streamlines the build process, but also highlights Zig's commitment to cross-platform compatibility, allowing developers to focus on writing code rather than tackling deployment issues. To summarize, Zig is a modern programming language that prioritizes performance, safety, and developer productivity. We've covered essential features including its robust performance through native compilation, manual memory management for safety, clear syntax for ease of use, modularity for better organization, and concurrency for efficient multitasking. Zig's community-driven nature also propels it as a language that adapts to the evolving needs of programmers. In our next lesson, we'll dive into advanced features of Zig, such as error handling and testing, which are critical for building robust applications. We'll explore how to properly address and manage errors in your Zig programs to enhance code reliability. Stay tuned, as we've only scratched the surface of what Zig can do for your software development. Now let's take a look at how to allocate memory for a list of game entities in Zig. In this example, we begin by importing the standard library, which provides essential functionalities for memory handling and debugging. The main function initializes the memory allocator, specifically opting for the page allocator, which is efficient for larger memory allocations. Next, we define the number of entities we want to create, in this case 100. Using the allocator alloc method, we allocate memory for these entities all at once, leveraging Zig's manual memory management capabilities. This is where Zig's focus on performance shines, as bulk allocation reduces fragmentation and enhances speed, crucial for applications like game engines that require real-time performance. If the memory allocation fails, we handle the error gracefully by outputting a debug message and terminating the function to prevent further execution. Then we proceed to initialize each entity in the allocated memory, setting their attributes such as id and name. Finally, it's important to free the allocated memory once it's no longer needed, which not only prevents memory leaks, but also showcases Zig's dedicated approach to manual memory management. Now let's see how we can implement effective error handling while working with files in Zig. In this example, we aim to open a file named example.txt for reading. Zig's error handling mechanism is elegantly captured using the catch expression, which allows us to manage errors without complicating our code. Initially, we attempt to open the file, and if the operation fails, the error is captured, and a meaningful message is printed to the debug console. This ensures that instead of the program crashing or silently failing, we get context on the failure, which is crucial for debugging. Next, once the file is opened successfully, we read its entire contents into memory using a function designed for this purpose. Again, we implement the catch mechanism here to manage potential reading errors, providing feedback if something goes wrong. Finally, if we successfully read the contents, we display them to the user. It's important to note that we also free the allocated memory after use, adhering to Zig's approach to manual memory management and avoiding memory leaks. This entire process showcases how Zig prioritizes safety and clarity in error handling, enhancing the robustness of our applications. Now let's take a look at how we can implement a simple recursive function to calculate the factorial of a number in Zig. In this code, we define a function named factorial that takes a single argument, n, of type U32. The function checks if n is equal to 0. If so, it returns 1, as the factorial of 0 is defined to be 1. For any other positive integer, it returns the product of n and the factorial of n1. This recursive approach is efficient for calculating factorials, showing how Zig's capabilities allow for straightforward function definitions. Next, we will write the main function, where we invoke our factorial function with the value 10, storing the result in a variable named result. To give feedback to the user, the program prints out the result using Zig's std debug print function, demonstrating not only the computation, but also Zig's strength in performance and native compilation. This simple yet effective example captures the essence of recursion and the language's power to produce optimized machine code for computational tasks. Now let's see how we can create and use a standalone module in Zig to promote modularity and code reusability. We begin by defining a simple mathematical function in a separate file named math.zig. This module features an exported function called add, which takes two integers as parameters and returns their sum. By exporting this function, we allow other files to utilize it, making our code more organized and manageable. Next, in the main.zig file, we import both the Zig standard library and our math.zig module using the @import statement. In the main function of our program, we call the add function from the math module, providing the integers 10 and 20 as arguments. The result of this addition is stored in the variable result. Finally, we use the std debug print function to display the result on the console. This clear separation of concerns simplifies our code structure, allowing us to work collaboratively on larger projects while enhancing the maintainability of our code. Now let's see how we can implement concurrent file downloading in Zig. In this example, we define a function called downloadFile that receives a URL as an argument. This function simulates the action of downloading a file by printing the URL to the debug output. While the real implementation would involve actual networking code, this simple print statement provides insight into the process. Next, we move to the main function, where we define an array of URLs representing the files we want to download. To effectively manage concurrency, Zig provides the std thread spawnAll function, which allows us to create multiple threads with ease. We pass it an array of pointers to the URLs and the downloadFile function to execute concurrently. Finally, we ensure all threads complete their operations by iterating over the spawned threads and calling their wait method. This approach not only facilitates simultaneous file access, but also simplifies the synchronization process without overwhelming our program with complexity. Through this example, we illustrate Zig's capabilities in handling concurrency efficiently, making it a powerful choice for modern applications. Zig's community-driven approach is another significant advantage. Being open source, the language is shaped by contributions from developers worldwide, ensuring continuous improvement and adaptation to the needs of the programming community. This flexibility means that Zig can incorporate new ideas and patterns that align with current development practices, keeping the language relevant. Additionally, the active community provides extensive documentation and a wealth of learning resources, making it much easier for new developers to dive into Zig. The beauty of being part of a community is that you never feel alone. You can easily find support, get your questions answered, and share your experiences. This collaborative environment fosters learning and innovation. Now let's see how we can define the target platform in Zig's build system to achieve cross-platform compatibility. In this example, we start by importing the necessary build module from Zig's standard library, which allows us to utilize its features for managing the build process. The build function is defined, which acts as the entry point for configuration. Inside this function, we access the target platform using btarget, which retrieves the specified target environment for which the application will be compiled. This flexibility is crucial for developers working in diverse environments, as it allows them to maintain a unified codebase. Next, we create an executable named myapp that will be compiled from the source file located at src/main.zig. The add-executable function facilitates this process by associating the name with the source code. To ensure that our application runs on the desired platform, we apply the target using exe set target target. Finally, the exe install method is called to install the generated executable, ensuring it is ready for execution on the target environment. This straightforward configuration streamlines the build process, making it a breeze to deploy applications across multiple platforms. In conclusion, Zig presents an exciting and robust programming language that integrates safety, performance, and developer productivity. We exploit its manual memory management, innovative error handling, impressive performance through native compilation, modular design for better code organization, and superior support for concurrent programming. The collaborative nature of its community and cross-platform compatibility further solidify Zig's growing status in the programming landscape. In our next lesson, we will dive into advanced topics such as testing in Zig and how to leverage its powerful testing capabilities to build more reliable applications. Stay tuned, and let's continue this journey into the world. Zig is a general-purpose programming language designed with a focus on performance, safety, and developer productivity. It is an exciting addition to the programming languages family, especially for those looking for a modern alternative to C and C++. Today, we will delve deep into Zig, exploring its features, benefits, and practical usage in real-world applications. Now let's see how we can implement a simple function in Zig that adds 2 integers. In this code snippet, we start by importing Zig's standard library, which provides essential functionalities, including debugging output. We then define a function named add that accepts 2 parameters, both of type 32-bit integers. This function performs a straightforward operation by returning the sum of these two integers. Next, we move to the main function, where we will utilize our add function. Inside main, we declare a variable named result and assign it the value returned by calling add with two specific integers, 5 and 7 in this case. This clearly showcases how we can use functions in Zig to encapsulate and reuse functionality. Finally, we use the std debug print function to output the result to the standard debug output. The format string, the sum is \n, dynamically incorporates the value of result, highlighting Zig's ability to perform clean and efficient string formatting. This simple example emphasizes the language's clear syntax while demonstrating its performance capability by executing a fundamental operation efficiently. Now let's see how we can implement manual memory management in Zig. In this example, we begin by importing the standard library, which provides necessary functionalities. We then define the main function, where we create an allocator using std heap page allocator, allowing us to allocate memory dynamically. Next, we calculate the size needed for an array of 4 integers and use the allocator to request memory for this array. It's important to handle any potential errors during allocation with the try keyword, which will return an error if the allocation fails. Once we have our allocated memory, we populate the array by assigning values to each element. The use of pointers here showcases Zig's ability to directly manipulate memory. We then iterate through the allocated memory, printing each integer value to demonstrate that our allocations were successful. Finally, we emphasize the importance of memory management by freeing the allocated memory with the allocator free (ptr) statement, which helps prevent memory leaks. This example effectively highlights Zig's focus on safety and control over memory usage, which is crucial for developing reliable software. Now let's take a look at how Zig facilitates modular programming with separate files. In the math.zig file, we define a simple function named multiply, which takes two 32-bit integer parameters, a and b, and returns their product. This modular function encapsulates a specific functionality, making it reusable across different parts of the application. Next, we will implement the main.zig file, where we begin by importing Zig's standard library for debugging outputs and the math module we just created. Inside the main function, we call the multiply function for math.zig with the values 4 and 5, storing the result in a variable named product. This illustrates how easily we can invoke functions defined in separate files, promoting a clean, organized structure in our code. Finally, we use std debug print to display the calculated product, showcasing Zig's straightforward syntax for printing output. This approach not only demonstrates how to manage dependencies between files, but also highlights the importance of modularity in keeping code bases manageable, especially as projects grow in complexity. Now let's implement a simple example to illustrate Zig's support for concurrency using asynchronous functions. We start by defining an asynchronous function called doWork, which simulates a task that takes time to complete. Within this function, the program prints a message indicating the start of the work and then simulates a delay by calling std time sleep for 1 second. This allows the main thread to be non-blocking, highlighting the beauty of concurrency in Zig, as the program can continue executing other tasks while waiting for the work to finish. Next, we move to the main function where we invoke doWork. Here, we create a handle for the asynchronous task, which allows us to manage the execution of that task. Immediately after triggering doWork, the program prints a message indicating that it's free to execute other operations. This is a key advantage of concurrent programming. Developers can design applications that remain responsive, enhancing overall performance and efficiency. Finally, we use await on the work handle to ensure that the program waits for the completion of doWork before finishing the execution, effectively synchronizing the tasks. This structure demonstrates how Zig equips developers with tools to handle multiple tasks concurrently, making it a powerful aspect of the language. Now let's see how we can implement a simple C function in Zig to compute the square of a number. We start with the C code, which defines a function called square that takes an integer as input and returns its square. This function simply multiplies the input by itself, demonstrating the straightforward nature of C syntax. Next, we will write the Zig code that integrates this C function. In our Zig program, we import the standard library using const std import std. To invoke the C function, we declare it using the extern keyword telling Zig that square is defined in the separate C file. This allows us to call square directly within our Zig code. Within the main function, we call square6 to calculate the square of the number 6, storing the result in the variable result. Finally, we use std debug print to output the result to the console, showcasing how easily Zig can interoperate with C code. This feature enhances development flexibility, allowing you to leverage existing C libraries seamlessly. Zig's community-driven development fosters a growing ecosystem of libraries and tools, enhancing its relevance in modern programming. With an active community contributing to its ongoing development, Zig constantly evolves to meet emerging needs. This means that while the core language remains simple, it is also extensible, allowing developers to build upon it without reinventing the wheel. The focus on simplicity and necessity ensures that only valuable features find their way into the language. The vibrant community serves as a support system, facilitating learning and making resources readily available for new developers looking to get started with Zig. To illustrate how the community can enhance productivity, let's say you want to build a web server. You could leverage existing libraries written in Zig, avoiding the need to start from scratch while maintaining all the performance benefits Zig has to offer. As we consolidate our understanding of Zig, let's recap what we've covered today. We explored Zig's performance and safety features, noting its native code compilation and manual memory management. We also discussed developer productivity, emphasizing its simple syntax and modularity, along with concurrency support and C interoperability. All these aspects contribute to Zig being a modern, powerful programming language for a wide range of applications. In our next lesson, we will dive into more advanced topics, specifically testing in Zig. Testing is a crucial part of software development, ensuring reliability and correctness in applications. We'll cover how Zig supports testing and best practices to help you produce robust applications. Zig is a modern, high-performance programming language that has garnered significant attention within the developer community. Its design stems from the desire to combine safety and productivity in a way that many developers have found appealing. Today, we will explore the history and philosophy behind Zig, providing insight into its inception, development, and what makes it unique in the programming landscape. So far, we have learned that Zig is a high-performance programming language that emphasizes safety and developer productivity through manual memory management and an intuitive syntax. We discussed its features such as native code compilation, modular design, support for concurrency, and interoperability with C, which enhance its applicability in various software development scenarios. The community-driven development of Zig ensures it remains relevant, providing resources and libraries to streamline the coding process. Now, we will talk about the history and philosophy of Zig, highlighting its origins and the principles that guide its development. Zig was created by Andrew Kelly, who previously worked on the Rust programming language. This background is significant because it showcases the influence that Rust had on Kelly as he ventured into designing Zig. While Rust emphasized safety primarily through its ownership model and strict compilation checks, Kelly aimed to create a language that retained performance and aimed for simplicity. The lessons learned from Rust were vital in shaping Zig, allowing Kelly to distill features he deemed necessary while leaving behind complexities that could create unnecessary barriers for developers. The design philosophy of Zig hinges on a few core principles. These include clarity, performance, safety, and robustness. Each principle plays a crucial role in making Zig appealing to developers, especially those who come from backgrounds steeped in C and C++. Performance is a key area of focus, and Zig upholds this by not abstracting away the hardware. When a developer writes Zig code, they are writing code that is essentially as close to the machine as it gets without resorting to assembly language. The compiler is designed to be smart and aggressive in optimizing code while providing predictable performance. Now let's see how we can implement manual memory management in Zig using a simple example. First, we import the standard library, which provides essential functions and types for memory allocation and other operations. In the main function, we define a variable allocator that utilizes Zig's page allocator for managing memory. We then declare the size of the array we want to allocate, which consists of 5 integers. Next, we dynamically allocate memory for the array using the allocator alloc method, which returns a pointer to the allocated memory. This highlights Zig's explicit memory management approach, allowing us complete control over memory life cycles. After successfully allocating the array, we initialize each element to 0 in a loop to prevent undefined behavior due to uninitialized values. We also print the value of each item for demonstration purposes, which allows us to confirm that our initialization has been successful. Finally, we remember to free the allocated memory using allocator free, showcasing the need for developers to be diligent in releasing resources when they are no longer needed. This example encapsulates Zig's philosophy of safety and performance through effective manual memory management. Now let's take a look at a simple function in Zig that checks whether a number is even or odd. This code exemplifies Zig's emphasis on clarity and straightforward syntax, making it easily understandable for developers. The function isEven takes a single parameter, number, which is of type i32, indicating that it can hold a 32-bit integer value. The return type is specified as bool, meaning it will return either true or false. Inside the function, the expression number%2 == 0 is used to determine if the number is even. Here, the modulus operator % calculates the remainder when number is divided by 2. If the remainder is 0, this indicates that the number is even, and the function returns true. Conversely, if the remainder is not 0, it returns false, indicating the number is odd. This function is not just concise, it also allows for immediate comprehension of its purpose. By writing such clear and direct code, developers can maintain focus on logic and problem-solving without unnecessary complexity or confusion, reflecting Zig's overall design philosophy aimed at enhancing code clarity. Now let's see how we can implement simple file I/O operations in Zig. In this example, we will open a file named example.txt using Zig's standard library, demonstrating the language's straightforward approach to cross-platform development. First, we call std_fs_cwd open file to create or open the file while specifying options to read, write, and create it if it doesn't exist. This ensures that our code remains flexible and resilient, accommodating various operating systems seamlessly. Next, we utilize the defer keyword to ensure the file is closed automatically once we are done with it, showcasing Zig's built-in resource management features that prioritize safety and cleanliness. After the file is opened successfully, we write a string hello Zig into it using file write_all. This operation exemplifies how easily Zig handles file writing. Subsequently, we read the entire contents of the file using read-to-end alloc, which allocates memory dynamically for storing the data. Finally, we print the contents of the file to the console with std debug print, providing a quick way to see the results of our file I/O operations. This example encapsulates Zig's capabilities and its developer-friendly design philosophy in facilitating cross-platform coding. Now let's take a look at how we can interoperate with C in Zig by using an external C function. In this example, we declare an extern function named C², which is intended to be defined in a C library. This declaration informs the Zig compiler that we will be using an external function to compute the square of a given integer. Next, we define the main function, which serves as the entry point of our program. Inside main, we invoke the C² function by passing the integer 7 as an argument, expecting it to return the square of this number. The result of this operation is stored in the variable result. Finally, we leverage Zig's standard library to print the output. The std debug print function formats the message to display the result, thus showing us the computed square of 7. This example highlights not only Zig's capability of seamlessly integrating C functions, but also how it maintains an idiomatic approach, making it efficient and straightforward for developers to utilize existing C libraries. Zig's community-driven approach is another cornerstone of its philosophy. The language actively encourages contributions from developers worldwide. This participatory environment fosters rapid development, allowing Zig to adapt to users' needs effectively. The collaborative spirit is apparent in how features are proposed, discussed, and eventually integrated into the language, making it a living entity rather than a static product. Consider the implementation of a new feature in Zig. It often begins within the community as a conversation around a need or a limitation. Developers share their experiences, discuss proposals, and iterate on solutions before they are officially integrated. This method bolsters the quality of the features that find their way into Zig and creates a sense of ownership among users. Now let's touch on the future of Zig. The continual evolution of the language aims to strike a balance between expanding capabilities while maintaining its core principles. The Zig development team is committed to refining the language based on user feedback, keeping an eye on emerging programming paradigms, and enhancing support for performance and safety. As we look ahead, you may wonder where Zig will fit into the programming landscape. Will it take hold among mainstream developers? Time will tell, but its unique approach to handling core programming challenges, with an emphasis on performance, safety, and developer productivity, gives it a robust foundation. Zig competes not just with C-like languages, but with any programming environment where performance is paramount. Zig's philosophy of providing a tool that doesn't compromise on performance while ensuring developers have the means to write clear and safe code is unlike any other language currently available. This dual focus on simplicity and capability will define its growth trajectory and further entrench its place among modern programming solutions. In summary, we've journeyed through the history and philosophy of the Zig programming language. We observed how Andrew Kelly's experience with Rust inspired the creation of Zig, which aims to provide performance, safety, and simplicity. We've discussed the significance of manual memory management, the clarity of syntax, cross-platform capabilities, interoperability with C, and the community-driven development approach that characterizes Zig. As the language continues to evolve, its commitment to these foundational principles positions it well for future growth and acceptance in the programming community. So, as we wrap up this discussion on Zig's history and philosophy, we approach our next lesson, where we will delve into testing in Zig. Testing plays an essential role in ensuring the reliability and correctness of applications, and we'll explore how Zig supports this crucial aspect of software development. Zig is a general-purpose programming language designed with a focus on performance, safety, and developer productivity. If you're familiar with languages like C and C++, you might find Zig to be a fascinating alternative that addresses some of the shortcomings of these traditional languages. Today, we will delve deeper into Zig and uncover its key features, advantages, and why it stands out as a modern programming language. So far, we've learned that Zig, developed by Andrew Kelly, combines performance, safety, and simplicity while being influenced by Kelly's experience with Rust. Key principles of Zig include manual memory management, clear syntax, cross-platform capabilities, and interoperability with C, enhancing developer productivity. We will further explore these foundational aspects of Zig to give you a comprehensive overview of the language itself. Now let's see how we can implement an iterative solution to compute Fibonacci numbers using Zig. In this code, we define a function called Fibonacci iter, which takes a single parameter, n, representing the position in the Fibonacci sequence we want to calculate. Within the function, we declare two variables, r and b, initialized to 0 and 1 respectively. These variables will hold the last two Fibonacci numbers as we iterate through the sequence. The core of the function is a loop that iterates from 0 up to n, non-inclusive. During each iteration, we temporarily store the current value of r in a variable named temp, then update a to be the value of b, and finally set b to the sum of temp and b. This logic effectively shifts the values of the Fibonacci sequence down the line, allowing us to generate the next number. After calculating the Fibonacci number, we return the value of a. In the main function, we set n to 10, call Fibonacci iter, and print out the result. This demonstrates not only the efficiency of the iterative approach, but also highlights Zig's native code compilation, ensuring a swift execution. Now let's see how we can manage memory safely in Zig by allocating and freeing a buffer. In this implementation, we start by importing the standard library to access its features, including memory allocation. Here, we use a page allocator, which allows us to request a specific amount of memory dynamically. Next, we define a constant for the buffer size and proceed to allocate memory for a buffer of 128 bytes. The try keyword is used here to handle any potential allocation errors gracefully, ensuring that the program does not crash unexpectedly. Once the buffer is successfully allocated, we populate it with data using a simple loop. Each element of the buffer is filled with indices cast to U8, demonstrating how direct memory access can be managed with precision. After performing any necessary operations with the buffer, such as printing its content, we must not forget to free the allocated memory. This step not only prevents memory leaks, but also emphasizes Zig's commitment to manual memory management, where the programmer maintains control over memory lifetimes. This careful approach minimizes unexpected behaviors in larger projects, showcasing Zig's focus on safety and efficiency. Now let's take a look at how to create a simple module in Zig. We begin by defining a module named math that encapsulates an add function. This function takes two integers as parameters and returns their sum. The use of the pub keyword exposes this function, allowing it to be accessed from other files or modules, promoting reusability. By organizing our code into modules like this, we can maintain clarity and structure in our projects, which is essential for large applications. Next, we can see how to utilize this module in another file. We start by importing the std library and our math module. In the main function, we call the add function from the math module by passing in two integers, 3 and 4. The result of this addition is then captured in the result variable. Finally, we print the result to the console using std debug print, illustrating the addition operation's output. This straightforward approach to module and function usage helps keep our code clean and efficient, demonstrating Zig's strengths in modular programming and developer productivity. Now let's see how we can compile our Zig programs for different architectures, enhancing cross-platform compatibility. The command utilizes the build.exe function, which instructs Zig to compile our source file, myprogram.zig, into an executable. By incorporating the target flag followed by a specific architecture, such as x86-64 Linux new, we ensure that Zig produces binaries suitable for the intended platform. This straightforward approach allows developers to write code once and easily adapt it for various operating systems like Windows, Linux, and macOS without needing extensive modifications. This feature is particularly advantageous in streamlining the development process, as it saves time and effort while maximizing the application's reach. By specifying the target during compilation, developers can ensure their programs operate seamlessly across different environments, which is crucial in today's diverse technology landscape. Thus, with this single compilation command, we can create an optimized binary that adheres to the needs of users on various platforms, highlighting Zig's versatility and efficiency in accommodating different systems effortlessly. Now let's take a look at how we can implement concurrent programming in Zig. In this example, we define a worker function that takes an identifier as an argument and simply prints out a message indicating which worker is currently running. This function showcases how straightforward it is to handle tasks simultaneously, allowing each worker to execute independently. Next, we define the main function where we create an array to hold 5 threads, each initialized to undefined at first. Within a loop, we use the std thread spawn method to create 5 concurrent threads, passing each thread a unique identifier. The catch block handles any potential errors that arise during this thread creation, ensuring that our program remains robust and responsive, even if something goes wrong. Finally, we wait for all threads to complete their tasks using the join method, which pauses the main thread until each worker thread has finished executing. This approach not only illustrates Zig's capability for concurrent execution, but also emphasizes how its standard library streamlines thread management, allowing developers to focus on their application logic with ease. As we wrap up this overview of Zig, it's important to recognize that the language is not just a new entrant in the programming world, but a thoughtful combination of performance, safety, developer productivity, and modern programming paradigms. Its ability to interoperate with C, extensive community-driven features, and clean syntax make it highly attractive for developers seeking better control without sacrificing effectiveness. Zig represents a significant leap forward, particularly for those coming from C and C++, while also appealing to newcomers looking for a reliable and efficient programming language. I encourage you to explore Zig further, play around with the code examples provided, and see how it can fit into your development toolkit. So far, we've learned about the core principles of Zig, including its performance, safety, and developer productivity aspects, illustrated through practical examples. Now, we will cover the role of testing in Zig to ensure application reliability and correctness in our next. Zig is a relatively new programming language, and it is natural to compare it to other popular languages to understand its place in the programming landscape. In today's discussion, we will explore how Zig stacks up against established languages like C, C++, Rust, and Go. So far, we've learned that Zig is a high-performance programming language emphasizing safety, manual memory management, and developer productivity. Key features include a clean syntax, cross-platform capabilities, and strong module support that enhances coding efficiency. We also explored how Zig compares to established languages and introduced its concurrency model. Now we will cover the comparisons in detail, emphasizing unique features, advantages, and drawbacks of each language. Now let's take a look at how we handle array access in Zig, emphasizing safety over undefined behavior. In the following snippet, we define a buffer with a fixed size of 10 unsigned bytes. It's important to note that while in C attempting to access an out-of-bounds index can cause unpredictable results, Zig's design proactively addresses this risk through runtime checks. Here, when we attempt to assign a value to buffer 10, which exceeds the allocated size, Zig triggers an array out-of-bounds panic. This immediate feedback alerts developers to the mistake, in stark contrast to C, where such an action would likely lead to a crash or security vulnerability. The code also includes a call to std debug print, which is used to output the contents of the buffer. However, due to the previous invalid access, this line would not be executed in practice. This demonstrates Zig's commitment to safety by ensuring that errors are caught early during program execution, making it a more secure choice for modern software development, especially in contexts where reliability is crucial. Now let's take a look at how we can implement a simple generics function in Zig. In this code, we define a function named sum, which is designed to accept two parameters of any type, specified at compile time using comtimet type. This allows the function to be highly versatile, enabling us to pass in different data types while retaining type safety. When we call the sum function with the specific type u32 and the values 5 and 10, it calculates the sum of these two integers. The type inference and compile time checks provided by Zig ensure that any errors related to type mismatches are caught before the code runs, which enhances overall code reliability. Finally, the result of the summation is stored in the result variable, and we use std debug print to neatly output the result. This approach not only makes the code concise, but also emphasizes the clarity Zig provides in working with generics compared to more complex template systems found in C++. The straightforward syntax and powerful capabilities can significantly boost developer productivity, allowing for easier code maintenance and implementation. Now let's implement a memory management example in Zig that showcases its direct control while ensuring safety. In this code, we begin by importing the standard library, which provides essential functionalities, including memory allocation. We define the main function, which is marked with a potential to return an error represented by the void type. Here, we create a variable for the memory allocator using std heap page allocator, which enables us to dynamically allocate memory. Next, we allocate a buffer of 10 bytes using allocator alloc. The try keyword is utilized to handle any potential errors during this allocation process gracefully. After successfully allocating memory, we proceed to fill our buffer using a simple loop. In each iteration, we assign values to the buffer, showcasing how straightforward it is to manipulate memory directly in Zig. To illustrate our results, we use std debug print to display the contents of the buffer. Finally, to emphasize the manual memory management aspect of Zig, we free the allocated memory with allocator free. This process illustrates Zig's balance between providing safety features and allowing developers complete control over memory, resembling a familiar approach to those coming from languages like C or C++. Now let's see how we can implement concurrency in Zig using threads. The code begins by importing the standard library, which provides necessary utilities for working with threads. We define a worker function that takes an identifier as a parameter and prints a message indicating which worker is currently running. This illustrates how multiple threads can execute independently yet cohesively. Next, in the main function, we declare an array to hold 5 thread instances. We then use a loop to spawn 5 threads, each executing the worker function with its unique identifier. If spawning a thread fails, we catch the error and print a failure message, ensuring that our program remains robust. After starting the threads, we utilize another loop to join each one. Joining a thread is crucial as it ensures that the main function waits for all threads to complete their execution before proceeding. This approach to handling concurrency emphasizes Zig's ability to manage threads directly without the overhead of a managed runtime, offering developers efficient control and performance. Through this example, you can appreciate how Zig's syntax remains simple while implementing powerful concurrency features. Now that we've delved into comparing Zig with other languages like C, C++, Rust, and Go, it's essential to discuss the community and ecosystem that revolve around these languages. C and C++ have extensive libraries and frameworks built over the years that offer mature solutions for various programming challenges. Rust has gained significant traction recently due to its strong emphasis on safety and community support, leading to an expanding set of libraries called crates. Zig's ecosystem is growing steadily, but it remains a newcomer compared to the giants of the programming world. Nevertheless, this youthfulness can also be beneficial, as it means developers can contribute to the community and shape its evolution. Zig's simplicity and clarity make it a delightful language for newcomers and experienced developers alike, allowing them to focus on problem-solving rather than wrestling with convoluted syntax. In terms of community involvement, new Zig developers can make a significant impact, participate in discussions, and contribute to libraries at an earlier stage than they might in more established language communities. This is a favorable environment for innovation and collaboration, fostering the development of unique libraries tailored to modern software challenges. As we wrap up our comparison of Zig with other programming languages, it is crucial to consider when best to use each language. C is an excellent choice for low-level systems programming and embedded systems where performance matters most. If you're working on performance-critical applications, C++ shines in scenarios where object-oriented design is necessary while providing access to powerful abstractions. Rust is your go-to language for safety and concurrency-heavy applications, particularly in systems where resource management and data integrity are paramount. Go would be the best pick for network services and applications requiring straightforward parallel programming without getting caught in intricate performance optimizations. On the other hand, Zig stands out when you need a blend of performance, safety, and clear syntax. Whether building systems-level software, tools, or even applications, Zig provides a modern approach that maintains the efficiency traditional developers love while minimizing common pitfalls associated with manual memory management. In conclusion, while every programming language has its strengths and weaknesses, Zig is carving out its niche as a straightforward language that emphasizes performance and safety without excessive complexity. Its ability to interoperate seamlessly with C, maintain low-level control, and provide a fresh perspective on generics and module management makes it an exciting option for new and seasoned developers alike. In our next lesson, we'll focus on the role of testing in Zig to ensure application reliability and correctness, building on the strong foundation we've established in our exploration of Zig's features and comparisons with other languages. Zig is a general-purpose programming language designed with a focus on performance, safety, and developer productivity. Unlike many modern languages, Zig shines through its simplicity and efficiency, making it a fascinating choice for both seasoned developers and newcomers alike. Today, we'll take a deep dive into Zig, exploring its features with practical examples and inviting you to see why it might be the next language you want to learn. So far, we learned that Zig is a high-performance programming language focused on safety, manual memory management, and developer productivity, and it compares favorably with established languages like C, C++, Rust, and Go. We explored key features of Zig, such as its clean syntax, safety improvements over C, simpler generics compared to C++, and straightforward memory management, making it attractive for developers. The discussion touched on how Zig handles concurrency with more efficiency than Go and the importance of its growing ecosystem. Lastly, we highlighted Zig's suitability for a variety of programming tasks, emphasizing its modern approach while minimizing complexity. Now, we will dive deeper into specific features of Zig, the syntax, and how you can start using it in your own projects. Now let's see how we can manage memory safely in Zig using the standard library's allocator. In the code, we start by importing the standard library, which provides essential functions and types for our program. We define the main function, which will return a special type indicating whether it completed successfully or encountered an error. Within the main function, we acquire a page allocator from the standard library. This allocator is responsible for allocating memory dynamically. We then proceed to allocate a block of memory for a buffer that can hold 128 bytes of unsigned 8-bit integers. The try keyword is crucial here. It attempts to allocate memory and passes any error back to the caller if it fails, ensuring that we handle potential allocation failures gracefully. Next, we use the defer statement to ensure that the allocated memory is freed when we are done with it, preventing memory leaks. After the allocation is successful, we can safely use the buffer to store and manipulate data. In this example, we store the characters H and I in the first two positions of the buffer and then print the content using the debug print function. This pattern exemplifies how Zig combines safety with manual memory management, giving developers control while reducing risks. Now let's take a look at a practical example of error handling in Zig through the implementation of a function that reads the contents of a specified file. The function readFile takes a file path as an argument and uses Zig's built-in file handling capabilities. Notice the use of the try keyword before the open file and read to end alloc calls. This indicates that the function may produce errors. If an error occurs at these points, control is passed back to the caller, rather than raising an exception, prompting the developer to handle the error explicitly. After successfully opening the file, we ensure that it is closed automatically using the defer statement, which guarantees that resources are properly released once they are no longer needed. Following that, we read the file's contents into a dynamically allocated array. The main function utilizes our readFile function, demonstrating how to handle errors effectively by once again using try. If reading the file is successful, the file's contents are printed to the console. Through this code, we see how Zig's approach fosters clarity and robustness in error handling, emphasizing developer responsibility in managing potential failures. Now let's see how we can leverage Zig's compile time features to compute values efficiently. In this example, we start by importing the standard library, which provides essential functionality. We then import the factorial function from the std math module, enabling us to calculate the factorial of a number. In the main function, we define a constant num assigned the value 5, which represents the number we want to calculate the factorial for. The key feature here is that we use the factorial function to compute the factorial of num at compile time. This means that instead of calculating the factorial during runtime, it is evaluated during the compilation process, which can significantly enhance performance. Finally, we print the result using std debug print, showcasing Zig's ability to handle formatted output seamlessly. This approach not only illustrates how Zig's compile time capabilities can optimize certain calculations, but also highlights its clear and concise syntax, making it accessible for developers at all skill levels. By utilizing such features, you can create efficient programs while maintaining readability and ease of understanding. Now let's take a look at a practical example of generics in Zig. The code defines a generic function called echo, which utilizes a compile time type parameter t. This function efficiently returns the value provided to it, showcasing how Zig implements generics with minimal syntax and overhead. By calling the echo function with different types, an integer and a floating point number, Zig's type inference capabilities come into play. The language automatically deduces the type based on the value passed, illustrating the flexibility of generics without complicating the syntax. This feature significantly enhances development productivity, making it easier for newcomers to grasp programming concepts without wading through intricate type hierarchies often found in other languages. In the main function, we see the invocation of echo for an integer 42 and a floating point number 3.14, followed by a formatted output of both results. This demonstration highlights how generics in Zig can seamlessly integrate with standard library functions like std debug print, making it a powerful tool for developers aiming to write clean, efficient code. Now let's see how we can implement concurrent tasks in Zig. The provided code demonstrates a clear and straightforward approach to handling multiple threads using Zig's concurrency model. First, we define a function called doWork, which accepts a unique identifier for each task. This function prints a message indicating when a task starts, and to simulate work, it pauses for 1 second before printing a completion message. In the main function, we create an array of threads to hold our tasks. The loop iterates over this array, and for each index, it spawns a new thread that executes the doWork function with the index as its parameter. This effectively creates several concurrent tasks that can run independently. After spawning the threads, the second loop ensures that the main program waits for all tasks to complete by calling taskWait on each thread. This mechanism is essential for synchronizing our program, as it allows the main function to pause execution until all spawned tasks finish their execution. This efficient and accessible concurrency model in Zig enhances productivity, allowing developers to create clean multi-threaded applications without unnecessary complexity. Now let's take a look at setting up a basic build system in Zig with a build.zig file. This file is crucial for defining how your application is built and managed. In the example, we start by importing the standard libraries build module, which provides the necessary functionalities for configuring builds. Next, we define a function called build, which accepts a pointer to a builder instance. This instance serves as a central point for our build tasks. Within this function, we then create an executable target named myapp, specifying that it will be built from the source file located at src/main.zig. This straightforward declaration helps streamline the build process. Finally, we call exec_install to ensure that after building, the executable is properly installed in the system, making it available for execution. By utilizing this basic setup, Zig's build system simplifies managing dependencies and builds, allowing developers to focus more on coding rather than on the intricacies of build configuration. It exemplifies how Zig provides robust tools that enhance productivity and ease of use. Also, the Zig community is vibrant and full of resources for learning and getting support. The official documentation is extensive, with a friendly community eager to help newcomers get started. By following Zig's spirit of simplicity and efficiency, you'll quickly find yourself writing high-performance code that is easy to read and maintain. To summarize, we've explored several of the fundamental features of Zig, including its focus on safety, efficient memory management, clear error handling, the simplicity of generics, and how it facilitates concurrency. We've seen how Zig's tooling and community support enhance the overall experience as a developer. Whether you're looking to write a system application, a game, or explore embedded systems programming, Zig stands out as a robust choice that meets modern development demands with a clean and approachable syntax. Going forward, if you want to dive deeper into Zig's capabilities, consider experimenting with its features in your projects. The language has much to offer, and as you grow more familiar with it, you will realize the advantages it brings over traditional programming languages. So grab your keyboard and start coding in Zig. Discover what this incredible language has. Now let's implement the following code to safely allocate and manage memory in Zig. First, we import the standard library, which provides essential functionalities, including memory management. The main function is defined as returning a result, indicated by the void type, which allows for error handling using Zig's try keyword. In this snippet, we declare an allocator using std heap page allocator, enabling us to allocate a specific amount of memory, in this case 128 bytes. The try keyword is crucial here as it checks for any potential errors during the allocation. If the allocation fails, it will automatically propagate the error upwards. After successfully allocating memory, we use the defer statement to ensure that the allocated buffer is freed automatically when it goes out of scope, thus preventing memory leaks. This approach emphasizes Zig's focus on manual memory management, allowing developers precise control over how and when memory is deallocated. Next, we proceed to manipulate the allocated memory by assigning values to the first 2 bytes and using std debug print to display the contents of the buffer. This demonstrates how simple and effective Zig makes manual memory management while maintaining safety and performance, key features that set it apart from garbage-collected languages. Now let's take a look at how we can implement file reading with explicit error handling in Zig. The function readFile takes a file path as input and attempts to open the specified file using the std fs cwd open file method. Notably, the use of the try keyword demonstrates Zig's approach to error handling. If the file cannot be opened, an error is immediately returned, forcing the caller to handle it. This explicit handling encourages developers to think critically about error possibilities and increases code robustness. Once the file is successfully opened, the defer statement ensures that the file is closed automatically at the end of the function, promoting good resource management. Next, we read the contents of the file into memory using file read-to-end alloc, again wrapped in a try to manage any potential allocation errors. The data read from the file is then returned to the caller. In the main function, we call readFile with example txt as the argument, and any errors encountered will propagate back to the caller, thanks to Zig's error handling mechanism. The successful read results in the contents being printed, providing a clear output to the user. This structured approach exemplifies Zig's focus on safety and clarity in error handling. Now let's see how we can compute the factorial of a number at compile time using Zig's powerful capabilities. In this code snippet, we start by importing the Zig standard library, which provides built-in functions and types for various tasks. We then import the mathfactorial function, which will be used to calculate the factorial. In the main function, we define a constant num and set it to 5, the number we want to compute the factorial for. By using the const keyword, we ensure that the value of fact is computed at compile time. This is significant because it allows the calculations to be completed before the program is executed, which enhances runtime performance and efficiency by eliminating unnecessary computations during execution. Finally, we use std debug print to output the result to the console, clearly showing the computed factorial of 5. This approach exemplifies how Zig's compile-time functionalities not only streamline code, but also optimize performance, making it easier to manage complex calculations without impacting runtime efficiency. Now let's take a look at a practical example of generics in Zig with a function called echo. This function demonstrates how you can leverage Zig's compile-time type safety while maintaining flexibility. The echo function accepts a type parameter t, which is specified using the comptime keyword. This means that the type t is resolved during compilation, allowing the same function to work with different types without losing the benefits of static typing. In the main function, we call echo twice, first with an integer i32, and then with a floating point number f32. Each call to echo passes a value of the corresponding type, showcasing how the same function can demonstrate type safety while being concise and adaptable. This feature not only leads to cleaner code, but also enhances performance, since type checking occurs at compile time, reducing the likelihood of runtime errors. By using generics, Zig allows us to write more reusable and maintainable code, which is particularly valuable in large projects where type management can become complex. Now let's implement a simple example demonstrating Zig's concurrency model by spawning multiple tasks. In this code, we define a function called doWork that will simulate a task by printing a message indicating it has started and then pausing execution for 1 second. This design allows us to illustrate how tasks can run concurrently without waiting for one to complete before starting another. Next, we set up the main function, where we create an array called tasks that can hold 5 threads. Using a loop, we initiate these threads with the std thread spawn method, passing the doWork function and the current index as arguments. This allows each thread to execute doWork independently, showcasing the concurrent execution capabilities of Zig. After we have spawned all the tasks, we need to ensure that the main program waits for each task to finish. We accomplish this with another loop that calls taskWait for each thread in the tasks array. This method blocks the main thread until the respective task is completed, illustrating how Zig efficiently manages concurrent tasks while avoiding unnecessary complexity in thread handling. Now let's take a look at how to set up a simple build configuration in Zig using a build.zig file. In this script, we begin by importing the standard library's build features through @import std build builder, which provides the tools necessary for managing the build process. Next, we define the build function that takes in a pointer to a builder. Within this function, we create an executable named myapp and specify its source file located at src/main.zig. The bead executable method facilitates this process by taking both the name of the executable and the path to the main source file, simplifying the task of defining project structure. After the executable is defined, we finalize the build configuration by invoking exec install, which indicates that the executable should be installed after it is built. This straightforward and declarative approach allows developers to manage their build environments efficiently, ensuring a smooth development workflow. By utilizing this concise configuration, you can focus more on writing your code rather than dealing with complex setup procedures, demonstrating one of Zig's core advantages in developer productivity. Moreover, the Zig community is one of its most valuable assets. The community is vibrant, welcoming, and eager to support both new and experienced developers alike. From the comprehensive official documentation to forums and social media groups, there are numerous resources to help you learn and grow your skills. Moreover, this community-driven aspect of Zig fosters a collaborative learning environment where developers can share tips, tricks, and examples that can help you navigate challenges in your projects. This support system lowers the barrier to entry for learning Zig and ensures you have resources at your disposal when diving into programming tasks. In conclusion, we've explored numerous features and benefits that make Zig an exciting language for developers. From its manual memory management and explicit error handling to compile-time capabilities, type safety, straightforward concurrency model, and robust tooling, Zig stands as a compelling choice in today's programming landscape. So whether you're looking to develop system applications, games, or delve into embedded programming, Zig offers the tools and community support to help you succeed. As you continue your journey with Zig, I encourage you to embrace its unique features, experiment with its capabilities, and contribute to the growing community. The future of programming is bright with Zig, and it's exciting to see how you will leverage this language in your coding. Zig is a general-purpose programming language designed with a focus on performance, safety, and developer productivity. Today, we're diving into the foundational aspects of Zig, exploring its core design principles and the reasons why it's becoming a go-to option for developers. Hold onto your seats because we're going to get into some engaging details, with plenty of examples to help clarify the concepts. So far, we learned that Zig is a programming language focused on safety, performance, and simplicity, appealing to developers with its manual memory management, explicit error handling, and compile-time functionalities. We examined how these features contribute to efficiency and code quality, along with Zig's unique approach to type safety and straightforward concurrency model. Additionally, the language offers a robust build system and a welcoming community that supports developers in their projects. These attributes position Zig as a compelling choice in the evolving programming landscape. Now we will talk about Zig's design philosophy and core tenets. The fundamental idea behind Zig is simplicity and control. Unlike many languages that abstract away details, Zig encourages programmers to understand what is happening under the hood. This hands-on approach not only fosters a deeper understanding of computer programming, but also gives developers fine-tuned control over their applications. From the ground up, Zig is built to ensure that developers maintain the ownership of their code, while having the tools they need to write efficient and safe programs. Now let's see how we can implement a memory allocation and deallocation routine in Zig. In this example, we begin by importing the standard library to utilize its built-in functionalities. We establish a memory allocator using std heap page allocator, which allows us to manage memory manually. Next, we define the size of the memory block we wish to allocate, 1 KB in this case. When we call the alloc function on our allocator, we specify the type of data we want to allocate, which is an array of U8 bytes. The catch statement here serves as an important safety feature, enabling us to handle any potential errors that may arise during memory allocation gracefully. If an error occurs, we print a message and exit the function to prevent further complications. Once we successfully allocate the memory, we fill it with zeros using std mem set, demonstrating how to initialize memory before use. Finally, we ensure to free the allocated memory at the end to prevent memory leaks, emphasizing Zig's commitment to explicit memory management and efficient resource usage throughout the program. Now let's take a look at how we can define and handle errors in Zig with a practical example. We start by creating a function named divide, which takes two integers as inputs and returns a floating point number. This function checks if the divisor is 0. If it is, instead of allowing a runtime exception to occur, it returns a custom error, divide by 0. This explicit error handling is a key feature of Zig, ensuring that potential issues are flagged at compile time rather than manifesting as bugs during execution. In the main function, we call divide with a numerator of 10 and a denominator of 0. The return value is assigned to result, which could either contain a valid floating point number or an error. We then use a switch statement to check the outcome of our division. If the error is divide by 0, we print a clear message explaining that dividing by 0 is not permissible. Conversely, if the division is successful, we print the result. This structure not only makes our code safer, but also encourages a proactive stance toward error management, showcasing how Zig elevates developers' ability to write robust applications. Now let's take a look at a simple compile time function that calculates the factorial of a number using Zig's unique capabilities. In this code, we define a recursive function named factorial, which computes the factorial for a given non-negative integer n. The function begins by checking if n is 0, in which case it returns 1, as the factorial of 0 is defined to be 1. If n is greater than 0, the function recursively calls itself with the argument n1, multiplying the current value of n by the result of this recursive call. Next, we implement the main function, where we call the factorial function with the argument 5 to compute 5 factorial, or 5. This computation occurs at compile time, meaning that the result is determined during the compilation process rather than at runtime, which enhances performance. Finally, the result is printed to the console using Zig's standard debugging print function. This capability of performing calculations at compile time exemplifies Zig's powerful metaprogramming features, which can significantly optimize performance in performance-critical applications. Now let's take a look at how Zig's type system operates through explicit conversions. In this example, we declare an integer variable x and a floating point variable y. To ensure precision during arithmetic operations, we explicitly convert the integer x to a floating point type f64 using the @int_to_float function. This requirement for explicit conversions prevents unintended type-related bugs that can occur in languages with implicit conversion rules. After performing the addition, we assign the result to z, which is also of type f64. Finally, we utilize std debug print to output the sum of x and y, along with the computed result z. This design not only enhances clarity, but also contributes to safer code execution at compile time, as the compiler can catch type mismatches and potential errors early in the development process. By embracing these practices, Zig allows developers to write more predictable and robust code, aligning with its overall philosophy of safety and efficiency. Now let's see how we can implement lightweight concurrency in Zig using threads. We start by defining a worker function that takes an identifier id, which it uses to print a message indicating that a worker is running. This demonstrates the simplicity of concurrent execution without blocking, as each worker operates independently of others. In the main function, we establish the number of worker threads we want to spawn, which in this case is set to 5. We create an array to hold the thread objects and utilize a loop to spawn each worker. For each iteration, we use std thread spawn to create a new thread and pass the worker function along with the current index, I. Proper error handling is implemented using a catch clause to manage any failures during thread creation, ensuring that if spawning a thread fails, we receive a useful message and exit gracefully. Lastly, after all threads are spawned, we join each worker thread in another loop to ensure that the main thread waits for their completion before exiting. This model emphasizes lightweight operations and allows us to efficiently handle multiple tasks without traditional locks, adhering to Zig's emphasis on safe concurrency. Now let's implement the following build script to understand how Zig's build system operates. This script starts by importing the standard build library, which provides essential tools for compiling our application. We define the build function, where we first obtain the default target and standard release options for our build configuration. This ensures that our application is compiled with the settings appropriate for the environment it's intended to run on. Next, we add an executable named myapp, specifying the source file that contains the entry point of our program. By calling exe set target target and exe set build mode mode, we link the executable to our chosen target and configure it with the specified build mode, which streamlines the compilation process. Lastly, we call b install artifact exe, which completes our build setup by installing the executable so it becomes readily available for execution. This cohesive approach minimizes configuration overhead, allowing developers to focus more on coding and less on complex build processes, reflecting Zig's core philosophy of simplicity and efficiency. As we wrap up our exploration of the foundations of Zig, we've covered its design philosophy, manual memory management, explicit error handling, compile time and runtime features, type safety, concurrency support, and the robust build system. Zig proves to be an impressive language for those seeking control and efficiency without sacrificing safety. With its unique features and welcoming community, Zig is making waves in the programming landscape. So whether you're developing low-level systems, building high-performance applications, or simply looking for a language that respects your developer intuition, Zig is worth your time and consideration. The journey doesn't stop here. Keep coding, experimenting, and pushing the boundaries of what's possible with this incredible language. Your next incredible project. Zig offers a compelling set of features that make it an attractive choice for developers. With its focus on performance, safety, and developer empowerment, Zig's design principles stand out in the crowded field of programming languages. In this session, we will expand upon the key features of Zig, illustrating how they facilitate efficient and robust software development. So far, we've learned about Zig's emphasis on manual memory management, explicit error handling, compile time functionalities, and its robust type system aimed at enhancing code predictability and efficiency. Now, we will cover the key features that make Zig a fascinating language for modern programming challenges. Now let's see how we can implement manual memory management in Zig. In this example, we first import the standard library to access built-in functions and types necessary for memory allocation. We utilize the page allocator from std heap, which allows us to allocate memory dynamically. Here, we specify a size of 512 bytes, a typical buffer size for many applications. Next, we use the allocator to request memory of type U8, which represents an array of unsigned 8-bit integers, and we handle any allocation failures using the catch syntax. If the allocation fails, the program prints an error message to the standard debug output and exits the function gracefully, ensuring that we do not encounter unexpected crashes. After successfully allocating the memory, we proceed to initialize the allocated block by setting all its bytes to a specific value using std mem set. This initialization step can be crucial in many scenarios, as uninitialized memory may lead to unpredictable behavior. Finally, we must remember to free the allocated memory with allocate-a-free memory to prevent memory leaks, reinforcing the importance of manual control in memory management within Zig. This reinforces how Zig empowers developers with explicit control over memory usage. Next, we will write the following code that demonstrates Zig's explicit error handling through a simple division operation. In the divide function, we are checking if the denominator y is 0. This is crucial because dividing by 0 is undefined and can lead to program crashes. Instead of allowing the program to fail silently or throwing an exception, we utilize Zig's error handling mechanisms to return a custom error named divide by 0. By explicitly handling this potential error case, we enhance the robustness of our code. In the main function, we intentionally call divide with the denominator set to 0 to trigger our error. The result of the divide function can either be a valid floating point number or an error. Here we employ a switch statement to handle both scenarios. If a divide by 0 error occurs, we print a clear error message to inform the user about the mistake. If the division were successful, we would print the resulting value. This approach not only keeps error management straightforward and transparent, but it also emphasizes the responsibility of the developer in managing error states explicitly, making it a vital learning point in writing safer and more reliable code. Now let's see how we can implement a compile-time factorial function in Zig. This code defines a recursive function named factorial that calculates the factorial of a non-negative integer provided as an argument. The function checks if the input n is 0, returning 1 if true, as the factorial of 0 is conventionally defined as 1. If n is not 0, the function recursively calls itself with the value of n1, thereby leveraging the recursive nature of the factorial calculation. In the main function, we invoke factorial 5, which computes the factorial of 5 at compile time. Zig optimizes this computation and evaluates it during the compilation process, meaning that the value is determined before the program even runs. The resulting value is then printed using std debug print, showcasing the power of compile-time evaluation to enhance performance. This example highlights how Zig's ability to perform computations at compile time can significantly improve the efficiency of your code, especially in more complex applications or large code bases, by eliminating the need for runtime calculations. Now let's see how we can implement a demonstration of Zig's robust type system. In this example, we begin by declaring an integer variable named int_value initialized with the value 10 and a floating point variable float_value set to 5. One of the key features of Zig is its emphasis on explicit type conversions, preventing automatic coercion between types. Here we explicitly convert the int value to a floating point number using the @int to float function before performing the addition with float value. This requirement for manual conversion not only fosters a better understanding of type handling, but also minimizes the risk of subtle bugs that can arise from unexpected type coercions. Afterward, we calculate the total of these two values and store it in a variable named total. The final step involves printing the result to the console using the standard library's debugging print function. By emphasizing explicit typing and manual conversions, this code enhances readability and predictability, key objectives in Zig's design philosophy. Such practices ensure that anyone reading the code can easily grasp what is happening without the confusion of implicit type changes. Now let's take a look at a simple example that demonstrates concurrency in Zig. The code defines a worker function, which is responsible for printing the ID of the worker that's currently running. This is a fundamental step in illustrating how we can manage concurrent tasks. In the main function, we specify the number of workers to create with the variable numWorkers. An array named workers is declared to hold the threads, initialized to an undefined state. Using a for loop, we iterate through the array of workers and spawn a new thread for each worker using std thread spawn. This function takes the worker function and the worker ID as arguments. An essential aspect of this implementation is the use of the catch block, which effectively handles any errors that might occur during thread creation, allowing the program to respond gracefully to failures. After all threads are spawned, we then join each worker thread in another loop, ensuring that the main thread waits for all workers to finish their tasks before exiting. This approach demonstrates how Zig promotes safe and straightforward concurrent programming practices, minimizing potential race conditions and deadlocks. Now let's see how we can implement a simple build system configuration in Zig. In this code, we begin by importing the builder from the standard library, which plays a crucial role in defining our build process. The function build takes a pointer to the builder as a parameter, allowing us to access various methods to manage the build. First, we configure the target architecture using bDefaultTarget, which automatically identifies the appropriate target for the build environment. Next, we specify the build mode with bStandardRelease options, enabling options tailored for release builds, such as optimizations for performance. Now we define our executable named myapp linked to the source file located at src/main.zig using b.add_executable. It's essential to set the target and build mode for the executable with exe set target target and exe set build mode, ensuring it builds correctly under the specified conditions. To finalize the setup, we call b-install artifact exe, which handles the installation of the compiled executable. This streamlined script illustrates how Zig's integrated build system simplifies project management, allowing developers to focus on coding without dealing with complex configurations. Throughout this exploration of Zig, we've delved into several key features that make it a compelling choice for developers looking to enhance their coding experience. From manual memory management and explicit error handling to powerful compile-time functionalities and a robust type system, Zig offers tools that transform the way we build software. Its simple concurrency model and efficient build system further emphasize control and minimize complexity. So far, we've covered the essential aspects that set Zig apart from other programming languages, and the fascinating facets we've examined provide a strong foundation for anyone looking to explore Zig further. As we continue our journey together into this exciting language, rest assured that there's much more waiting on the horizon. Zig is not just a language, it's a reliable tool to empower developers in navigating the modern programming world. Zig is a general-purpose programming language designed with a focus on performance, safety, and developer productivity. It aims to be a modern alternative to languages like C and C++, allowing developers to write efficient and reliable code without losing control over system resources. Now let's see how we can implement memory management in Zig using the standard heap allocator. In this example, we first acquire the std heap c allocator, which provides a way to dynamically allocate memory. We then allocate 10 bytes for a buffer using the allocator alloc method, which returns an error if the allocation fails. This is where the use of the try keyword becomes essential. It allows us to handle any potential errors gracefully. Next, to ensure that we don't create memory leaks, we utilize the defer statement, which guarantees that the allocated memory will be freed when it is no longer needed. This is a crucial aspect of manual memory management, ensuring that resources are properly released. Finally, we print the allocated buffer's address in hexadecimal format using std debug print. This demonstrates how we can effectively manage memory in Zig while maintaining full control over allocation and deallocation, ultimately leading to safer and more efficient applications. Now let's see how we can implement manual memory management in Zig. To begin, we acquire the standard heap allocator using std heap c allocator, which provides us with the necessary tools to allocate and free memory. Next, we use the allocator alloc method to allocate 10 bytes for our buffer, and we apply the try keyword to handle any potential allocation errors gracefully. This error handling is crucial in ensuring our program remains robust. Once the memory is allocated, we utilize the defer statement to guarantee that the memory will be freed once it is no longer in use, thus preventing memory leaks, which can occur easily with manual management. This is a significant feature of Zig's design, as it empowers developers to maintain memory safety without resorting to garbage collection. Finally, we use std debug print to output the allocated memory's address in hexadecimal format. This not only serves as a confirmation of our allocation, but also demonstrates how memory management in Zig allows for direct interaction and inspection of system resources, essential for high-performance applications. Now let's take a look at how error handling is implemented in Zig, showcasing its explicit model that promotes robust programming practices. We begin by defining a function called mayFail, which deliberately returns an error of type error, some error. This method allows us to signal issues that the calling function can subsequently manage. In the main function, we incorporate error handling by calling mayFail. The use of an if statement checks the result of this function. If an error is encountered, it is captured in the variable error. This enables us to handle errors gracefully, as we can print a message to the console that includes the specific error encountered. This design pattern ensures that we acknowledge all possible error outcomes, fulfilling Zig's commitment to explicit error management. If mayFail executes successfully, we print a confirmation message indicating that no errors occurred. This structured approach not only informs users about potential issues, but also enforces a discipline in coding that encourages thorough consideration of error states, ultimately leading to more stable and reliable applications. Now let's take a look at how we can implement a recursive function to compute the factorial of a number in Zig. The function compute factorial is defined to take a single argument, n, of type U32. It checks if n is 0, in which case it returns 1, as the factorial of 0 is defined to be 1. If n is not 0, the function calls itself with n1, multiplying the result by n for the factorial calculation. This recursive approach allows the compiler to evaluate the function at compile time when invoked with a constant expression, leading to performance optimizations. In the main function, we invoke compute factorial with the argument 5, which will compute the factorial of 5. The result is then printed out using std debug print, demonstrating how effectively Zig can handle computations at compile time to create faster binaries. This showcases one of the significant advantages of Zig, the ability to optimize and reduce runtime overhead through compile time execution. Now let's take a look at how we can define a simple struct in Zig, showcasing its robust type system. We begin by creating a user profile struct that encapsulates a user's name and age. The struct has two fields, name, which is a slice of constant unsigned 8-bit integers, and age, which is a 32-bit unsigned integer. This static declaration ensures that any variable assigned to these fields adheres to the specified types, reinforcing type safety at compile time. Next, we implement a main function where we create an instance of user profile, initializing it with values for name and age. Here, we utilize Zig syntax for struct instantiation, which clearly sets the values for each field. Afterward, we utilize the standard library's debugging function to print out the user's information. This step illustrates how Zig's type system helps prevent type-related errors by enforcing the correct type assignments, enhancing reliability, and making the code easier to understand. Overall, struct definitions in Zig serve as a powerful tool for modeling complex data structures while ensuring safety and clarity. Now let's implement a modular approach by creating a mathematics module in Zig. We begin with the definition of a simple function, add, which takes two integer parameters a and b and returns their sum. This function encapsulates the addition operation, promoting code reuse and maintaining a clean structure in our codebase. Next, we transition to the main program where we'll utilize this module. By importing math.zig, we gain access to the add function, which allows us to call it within our main function. Upon invoking math add 5, 7, the result of adding these two numbers is stored in a variable named result. This showcases Zig's straightforward syntax for function calls and variable assignment. Finally, we use the standard library's std debug print function to output the result to the console, effectively demonstrating how modularity enhances readability and organization. This approach not only aids in collaboration, but also makes larger projects easier to manage, highlighting the advantages of Zig's strong module system in developing maintainable code. Now let's see how we can implement concurrency in Zig with a simple example. In this code, we begin by defining an asynchronous task, a sync task, which takes a compile time identifier and prints out its running status. This simple function exemplifies how tasks can be defined in a concurrent context. Next, in the main function, we declare an array called tasks to hold references to threads we'll spawn. We then use a loop to iterate through this array, where each iteration spawns a new thread for the async task, passing the current index as the task identifier. If the thread is successfully created, we store its reference in the tasks array. This structure allows us to create multiple threads effortlessly without the intricate boilerplate often associated with traditional threading. After spawning all the tasks, we include another loop to wait for each of these threads to complete their execution. This ensures that the main program does not terminate until all asynchronous tasks have finished running. Overall, this example demonstrates how Zig simplifies concurrent programming while enhancing the ease of execution and performance in applications. Now let's implement a build configuration using Zig's integrated build system. In this example, we begin by importing the necessary components from the standard library, particularly the builder class. The build function serves as the entry point for setting up our build process. Within this function, we create an executable named myapp by calling b@executable, specifying the output name and the path to our main source file. Next, we define the target platform for our executable, setting it to Windows using the setTarget method. This specific configuration ensures that the generated executable will run smoothly on the Windows operating system. Additionally, we specify the build mode by setting it to build mode, release fast, which optimizes the executable for performance by applying release-level optimizations. Finally, we call binstall executable to complete the setup, registering the executable so that it can be built and installed effectively. This streamlined setup process exemplifies how Zig's build system simplifies dependency management and enhances developer productivity when working on complex projects. As we conclude our introduction to Zig, it's essential to recognize its strong community-driven development model. Zig is open source, and its evolution relies heavily on community contributions. This collaborative spirit fosters the addition of features and enhancements based on real-world developer needs. With its focus on performance, safety, simplicity, and developer productivity, Zig is emerging as a compelling choice for modern software development. Whether you are developing systems-level applications, game engines, or anything in between, Zig provides a robust, flexible, and efficient option. In the next session, we will dive into specific features of Zig that enhance its safety and concurrency aspects even further, providing deeper insights into its powerful capabilities. Make sure to stay tuned as we continue exploring the potentials of this innovative programming language. Zig offers a compelling set of features that make it an attractive choice for developers seeking performance, safety, and a robust programming experience. In this exploration of Zig, we will dive into its multifaceted capabilities, showcasing how its design philosophy empowers developers to create high-quality software efficiently. So far, we learned about Zig as a general-purpose programming language focused on performance, safety, and developer productivity, with features like manual memory management and explicit error handling. We have explored its capabilities in native code compilation, type safety, modular programming, and concurrency, along with its integrated build system that simplifies project management. Now we will delve deeper into Zig's features, highlighting manual memory management, safety guarantees, effective error handling, and its powerful type system. Now let's see how we can implement manual memory management in Zig using the built-in allocator. In this example, we first import the standard library, which provides essential functionalities, including memory allocation. We then define the main function, which is the entry point of our program. Inside the main function, we utilize the page allocator from Zig's standard library to dynamically request a block of memory. Specifically, we allocate 1024 bytes and store the starting address in the variable buffer. It's important to handle potential memory allocation failures, so we use the try keyword, which propagates any errors that may occur during allocation. To prevent memory leaks, we incorporate the defer statement, which ensures the allocated memory is automatically freed once it goes out of scope, maintaining a balance between control and safety. Finally, we print the memory address of the allocated buffer using Zig's debug print functionality. This implementation not only showcases Zig's straightforward approach to manual memory management, but also emphasizes its built-in safety features that help manage resources effectively. Now let's see how we can manage null pointers safely in Zig. In the code, we define a function called safety_reference that takes a nullable pointer as its parameter. This function leverages Zig's safety features by checking if the pointer is null before dereferencing it. If the pointer is valid, it proceeds to dereference and return the value safely. However, if the pointer is null, it returns an explicit error indicating a null pointer dereference, rather than allowing a crash due to undefined behavior. Within the main function, we initialize a nullable pointer buffer to null, emulating an uninitialized state. When we attempt to dereference buffer using the safety_reference function, we use the try keyword to handle any potential error gracefully. This approach not only demonstrates how Zig enforces safe practices when dealing with pointers, but also ensures that developers proactively address potential issues. By having to explicitly check for null pointers, Zig helps mitigate common problems such as segmentation faults, thereby improving overall code safety and reliability. Now let's take a look at Zig's explicit error handling model, which significantly enhances code safety and clarity. In the provided example, we define a custom error type called myError, which represents the potential errors that can occur in our program. Next, we create a function named mayFail that is annotated with a to indicate it can return an error value. In this case, mayFail deliberately returns the myError when it's invoked, showcasing how functions can signal errors. In the main function, we utilize the try statement when calling mayFail. This statement automatically checks for errors returned by mayFail and will handle them by exiting the function if an error occurs. This immediate error handling prevents any further execution of code that might depend on the successful completion of mayFail. It exemplifies how Zig's model simplifies error management, allowing developers to focus on writing cleaner and more robust code. If there are no errors, the program will proceed to print a message indicating that the code after the try statement will not be executed in case of an error, reinforcing the importance of error handling in the function's flow. Now let's take a look at how we can leverage Zig's type system by creating a type alias to improve code clarity. In this example, we define a type alias called meta that represents a floating point number, specifically F64. This abstraction helps to differentiate meta values from other numeric types in our program, promoting more readable and maintainable code. Next, we will implement a function named convert_to_kilometers, which takes a distance in meters as input and returns the equivalent distance in kilometers by dividing the input value by 1000. This clear conversion mechanism exemplifies how type aliases can aid in preventing logical errors, particularly in cases where multiple units might be used interchangeably. Within the main function, we specify a constant distance in meters with a value of 500, representing our input in meters. We directly call convert_to_kilometers using this value to calculate the distance in kilometers, which is then printed to the console. This implementation highlights the significance of using type aliases in fostering data integrity and readability, especially in complex applications where measurement units are critical. Now let's take a look at how we can implement a simple geometry module in Zig that calculates the area of a circle. In the geometry Zig file, we define a public function named area_of_circle, which takes a single parameter, radius, of type F64. The function uses the mathematical constant pi from the standard library to calculate the area by multiplying pi with the square of the radius. This straightforward calculation encapsulates a common geometric formula while promoting modularity by isolating functionality into separate files. Next, we will write the main function in the main.zig file, where we begin by importing the standard library and our newly created geometry module. Inside the main function, we declare a constant for the radius and assign it a value of 5. We then call the area_of_circle function from the geometry module, passing in the radius, and store the resulting area in a constant. Finally, the program prints the area of the circle, demonstrating how easy it is to reuse the calculations defined in our module. This modular setup not only aids in code organization, but also enhances collaboration among developers working on larger projects. Now let's take a look at how we can implement concurrency in Zig through the use of threads. In this example, we define a function called task, which represents a simple unit of work that each thread will execute. This function begins by printing a message indicating the start of the task, then simulates some processing time by using a sleep function to pause execution for 1 second. This provides a way to visualize the concurrency in action, as multiple tasks will overlap during their execution. Next, we set up the main function, where we define the number of threads to spawn. An array called threads is created to hold the thread instances. Using a for loop, we iterate over the threads and spawn each one, passing the task function along with a unique identifier for that thread. This allows each thread to work concurrently on the assigned task without blocking the others. Lastly, we wait for all threads to complete their execution using another loop, ensuring that the main program does not exit until every task has finished. This straightforward approach illustrates how Zig simplifies thread management while maintaining readable syntax, empowering developers to harness the full power of multi-core processes effectively. Now let's see how we can implement a basic build configuration in Zig using the build.zig file. In this example, we start by importing the builder from the standard library, which is essential for setting up our build process. We then define a public function named build that takes a pointer to the builder as a parameter. This function is where we specify all the necessary details for our executable. We first add an executable using the addExecutable method, setting its name to myapp and pointing to the source file located at src/main.zig. This straightforward approach allows us to clearly define what our main program file is. Next, we designate the target operating system for our build by calling setTargetos and specifying that we are targeting Linux. Additionally, we optimize our build for performance by setting the build mode to release fast, which is particularly useful for production environments where speed is critical. Finally, we use the install_executable method to register our executable for installation. This configuration not only simplifies the build process, but also allows developers to focus more on coding rather than managing complex scripts. As we conclude our discussion on Zig's prominent features, it's clear that its design philosophy emphasizes performance, safety, and productivity. With manual memory management, robust safety guarantees, and a straightforward error handling model, Zig empowers developers to build efficient and reliable applications. The powerful type system and modular programming capabilities foster maintainable code, while its concurrency features and integrated build system simplify the development lifecycle. In this lesson, we've taken an in-depth look at how these features benefit developers and enhance their productivity, making Zig not just a programming language, but a modern tool for efficient software development. In our next lesson, we will continue to explore more advanced aspects of Zig, particularly focusing on the new developments enhancing its capabilities in safety and concurrency, so stay tuned. Zig is a general-purpose programming language designed with a focus on performance, safety, and developer productivity. In this tutorial, we'll dive deeper into the fascinating benefits and features that make Zig stand out in the world of programming languages. So far, we've learned that Zig emphasizes performance, safety, and productivity through features like manual memory management, compile-time safety checks, and a unique error handling model. We've explored its strong type system, modular programming capabilities, and effective concurrency support, all contributing to building efficient applications. Additionally, we discussed Zig's integrated build system that simplifies project management, allowing developers to focus more on coding. Now we will explore Zig's benefits in detail, including its simplicity, error handling, and tooling, providing you with a comprehensive understanding of what makes Zig an exciting choice for developers. Now let's take a look at a simple yet effective example demonstrating Zig's syntax and standard library. In this snippet, we start by importing Zig's standard library, emphasizing how easy it is to access built-in functions and structures. We then define a main function, which is the entry point of any Zig application. Inside the main function, we utilize the standard output writer obtained from the standard library, showcasing Zig's clean and concise approach to coding. Notice how we call the print method on the output writer, allowing us to display the message "Hello, Zig" to the console. This particular line highlights the clarity and straightforwardness of Zig's syntax. There are no complex constructs or verbose definitions, making the code extremely readable. The catch statement gracefully handles any potential errors that may arise during the printing process, which exemplifies Zig's design philosophy of maintaining safety without compromising on simplicity. This straightforward example not only shows how to write a basic program in Zig, but also reflects the language's commitment to reducing cognitive load, enabling developers to focus on what truly matters, solving problems efficiently. Now let's see how we can implement manual memory management in Zig. In this example, we start by using Zig's page allocator to allocate memory for an array of 1024 bytes. This choice allows us to manage memory efficiently while ensuring safety, as we can explicitly control the lifecycle of our memory allocation. We utilize the defer statement to ensure that the memory is released properly once it is no longer needed. This prevents memory leaks and dangling pointers, which are common pitfalls in many programming languages. The loop iterates over the allocated memory, initializing each byte to 0, showcasing how we can work with raw memory directly while still maintaining safety. Finally, we use std, debug, print to confirm the successful allocation and initialization of memory, providing valuable feedback during development. This snippet highlights Zig's ability to combine manual memory control with compile-time safety checks, making it an excellent choice for developers who require both performance and safety in their applications. Next, we will explore a practical implementation of Zig's explicit error handling model. In this example, we define an openFile function that tries to open a file specified by the given path. The use of try within this function attempts to execute the file opening operation. If it fails, an error is returned rather than throwing an exception. This approach makes error handling clear and straightforward, as it becomes the caller's responsibility to handle the potential error. Now let's see how we can implement the error handling in the main function. We call the openFile function with the path to data, txt, and utilize a catch block to manage any errors that occur. If the file fails to open, a descriptive error message is printed to the console, allowing developers to diagnose issues easily. This explicit handling leads to more readable and maintainable code because the flow of error handling is explicitly defined. On successful file opening, the program confirms the operation with a printed message, demonstrating how effectively Zig promotes robust error management. Now let's see how we can implement a function to compute the factorial of a number using recursion in Zig. The factorial function takes an unsigned 32-bit integer as input and checks if the value is 0. If so, it returns 1, as the factorial of 0 is defined as 1. If the input is greater than 0, the function recursively calls itself with the input decremented by 1, effectively breaking the problem down into smaller subproblems. This recursive approach elegantly illustrates how complex calculations can be simplified. In the main function, we declare a constant named result that assigns the output of factorial 5. Here, the factorial of 5 is computed, resulting in 120. This value is then printed to the console using std debug print, demonstrating not only the functionality of the factorial function, but also Zig's ability to handle computations at compile time. By preprocessing known values when building the program, Zig optimizes performance, as the compiler can substitute this precomputed value directly into the binary, ensuring an efficient runtime execution. This exemplifies one of Zig's powerful features, allowing developers to perform such calculations during compilation. Now let's see how we can implement a simple asynchronous operation in Zig. The fetchData function serves as a simulated asynchronous task for fetching data using Zig's concurrency model. Inside this function, a debug print command notifies us when data fetching starts, providing a clear indication of the operation's flow. Next, in the main function, we invoke fetchData, utilizing Zig's unique error handling approach. By using the catch statement, we elegantly handle any errors that might occur during the fetch operation. If any error is encountered, it prints the error message to aid in debugging and gracefully exits the function to prevent further execution. This explicit error handling promotes clarity and robustness in your code, ensuring that you know exactly where and why something went wrong. If the operation is successful, a confirmation message is printed, signaling that the data fetch was completed without issues. This straightforward method of managing asynchronous operations in Zig highlights the language's focus on safety and simplicity, making concurrent programming approachable even for those new to the concept. Now let's implement a simple addition function along with a corresponding test case in Zig. This code defines a function named add, which takes two unsigned 32-bit integers as parameters and returns their sum. By providing an explicit function for addition, we can maintain clarity in our operations and ensure our code remains readable. Next, we incorporate the testing capabilities of Zig by defining a test labeled addition test. Inside this test, we call the add function with the values 2 and 3 and store the result. We then define the expected outcome, which is 5, and use Zig's built-in testing framework to assert that the result of our addition matches this expectation. If the condition is true, it confirms that our function works as intended. Otherwise, the test will fail, alerting us to potential issues. This integration of a testing framework encourages a test-driven development approach, ensuring that we can continuously validate our code as we develop, ultimately leading to higher code quality and reliability. Through this example, we demonstrate not only how to implement functionality, but also how to maintain robust testing practices within our development process. Now let's take a look at an optimized implementation of the factorial calculation in Zig, which showcases the language's performance capabilities through the use of loops instead of the more conventional recursion. By defining the factorial function to take a 32-bit unsigned integer, we initialize the result to 1 and use a loop to multiply the result by each integer from 1 to n. This iterative approach increases efficiency by minimizing function call overhead and stack depth associated with recursion. In the main function, we declare a constant variable num set to 10, which represents the number for which we will calculate the factorial. The factorial function is then invoked with this value, and the result is printed to the console, demonstrating the effective performance of Zig in handling computational tasks. By leveraging loop constructs, this example highlights how Zig's low-level nature allows developers to write code that executes faster and avoids potential pitfalls of recursion, reaffirming why Zig shines in performance-critical scenarios. Now let's take a look at Zig's integrated build system, which streamlines the project management process by working closely with the compiler. In the provided code, we define a build function that takes a builder object as a parameter. This function is essential for creating an executable program within Zig. First, we use the addExecutable method of the builder to specify the name of the executable, my program, which will be constructed from the source file src/main.zig. This approach simplifies file referencing, making it easier to manage your source code structure without dealing with external scripts or configurations. Next, we set the target and build mode for the executable using the setTarget and setBuildMode methods, respectively. This allows the program to be compiled specifically for the intended architecture and performance mode, ensuring optimal execution. Finally, by calling the install method, we finalize the setup, enabling the executable to be installed in the appropriate location. This elegant build structure allows developers to focus on writing code rather than getting entangled in complex build processes, reflecting Zig's commitment to enhancing development productivity. In summary, Zig offers a robust programming experience centered around performance, simplicity, and safety. By embracing manual memory management, explicit error handling, compile time capabilities, and an integrated build system, Zig empowers developers to write clearer, more efficient code. So far, we've covered the essence of what makes Zig exceptional, from its syntax and memory management to its powerful concurrency model. Moving forward, we will delve even deeper into advanced features that further enhance Zig's capabilities and applications as we continue our exploration of this remarkable programming language. As we conclude this lesson, I encourage you to experiment with these features in Zig. There's a vibrant community and plenty of resources available that can assist you in your journey as you explore this language further. Whether you are a beginner or an experienced programmer, Zig offers you tools and techniques that not only enhance efficiency, but also promote a new way of thinking about programming itself. Stay curious, keep coding, and I'll see you in the next. Zig is an intriguing programming language that stands out with its unique focus on performance, safety, and developer productivity. Today, as we explore the Zig programming language deeper, you're going to discover the features that make this language a great choice for various applications, whether it be systems programming, game development, or even scientific computations. So far, we covered the foundational concepts surrounding Zig, including its simplicity in syntax, manual memory management, and unique error handling capabilities. We've also highlighted its robust integrated build system, compile time features, and concurrency model that aids in writing clear and efficient code. Now, we will delve into its advanced features and practical applications, enhancing your understanding of how Zig can be effectively employed in real-world scenarios. Now let's take a look at a simple Zig program that showcases how to use the standard library for input and output operations. In this example, we begin by importing the standard library with the @import statement, which allows us to access various functionalities provided by Zig's core library. We then define a main function, which serves as the entry point for the program. Within this function, we create a stdout variable that utilizes the std, or get std out, writer, to obtain the standard output writer. This writer will enable us to print text to the console easily. Next, we employ the try keyword followed by the stdout print function to print the message "Hello, Zig" to the console. The use of try allows us to handle any potential errors that might arise during this operation, ensuring that our program remains robust and reliable. By simply invoking this function, we can see how concise and effective Zig syntax is for performing basic I/O tasks, demonstrating its focus on both simplicity and performance in coding. Now let's see how we can implement optional types in Zig to enhance safety when dealing with potentially null values. The getNullableValue function is designed to return an optional integer, defined by the return type U32. This indicates that the function may return either a U32 value or a null. Inside the function, we evaluate whether a specific condition is true. If it is, we return the integer value 42. Otherwise, we return null. This pattern allows for clearer handling of situations where a value may not be present. Next, we observe the main function, where we call getNullableValue and check if a value has been returned. The ifValue construct signifies that if value is not null, we can safely access the actual integer, v, and print it. If value is null, indicating no value was returned, we print a different message. This approach minimizes the chances of null-pointed dereferences, reinforcing the safety features Zig offers. By utilizing optional values, we create more reliable programs while keeping the code straightforward and intuitive. Now let's see how we can implement asynchronous operations in Zig to enhance our application's responsiveness. In the code snippet provided, we define an async task function that simulates a non-blocking task by printing a message. The key here is that while this task is executing, the main function doesn't wait for it to finish. Instead, it continues to execute its own commands, as seen in the main function where we call tryAsyncTask, followed by another print statement. This structure illustrates how Zig's concurrency model allows operations to be handled simultaneously, optimizing CPU utilization and maintaining user interaction without interruptions. The non-blocking nature of this approach is crucial for creating efficient applications, enabling developers to design systems that remain responsive even when executing longer tasks. By leveraging async functions and the associated syntax, Zig makes concurrent programming intuitive and accessible, allowing you to create more dynamic applications effortlessly. This is just one example of how Zig can help streamline complex operations and improve overall performance in your projects. Now let's see how we can manage memory effectively in Zig. In this example, we begin by importing the standard library, which provides essential functionalities including memory management. The main function is defined with the potential to return an error, indicated by the void return type. Inside this function, we create a variable that points to Zig's page allocator, which is responsible for efficiently allocating memory. Next, we allocate 1 KB of memory using the alloc method, specifying that we want an array of unsigned 8-bit integers. The try keyword is crucial here as it handles any errors that may occur during allocation, ensuring that our program remains robust. After successfully allocating memory, we use the defer keyword to ensure the allocated memory is freed automatically when the main function exits. This demonstrates Zig's commitment to safety by managing memory without requiring the programmer to explicitly remember to free it, reducing the potential for memory leaks. Finally, we can assume that the allocated data would be utilized further in the program, showcasing the simplicity and power of Zig's memory management features. Now let's implement a simple module in Zig to demonstrate clean code organization and modular programming concepts. We begin by creating a separate file called my_module_zig, where we define our module. Inside this module, we declare a public function named greet. This function uses Zig's standard library, imported through @import std, to print a greeting message to the console. Next, we will see how we can utilize this module in our main program. In the main.zig file, we again use the @import statement to bring in the functionality of our my_module_zig file. This allows us to access the greet function defined in the module. In the main function, we simply call my_module_greet, which invokes the greeting message. This approach exemplifies the modularity in Zig, showcasing how we can separate functionalities into distinct files. By using modules, we enhance code organization, making it easier to manage and scale our applications as they grow in complexity. This method encourages clean code practices and fosters maintainability across different components of your project. Now let's take a look at how Zig can seamlessly integrate with existing C libraries using native interop capabilities. In our example, we first import the standard library, which provides access to essential functionalities in Zig. Next, we declare an external C function called printf, enabling us to leverage this standard output function from the C library directly in our Zig code. This use of the extern C block illustrates how we can call C functions without rewriting or adapting existing infrastructure, a major benefit when transitioning codebases to Zig. In the main function, we use print to print a simple message, "Hello from Zig with C." This line showcases the straightforward syntax Zig provides for invoking external functions. By integrating with C, we gain the ability to harness the wealth of libraries and functions available in C while benefiting from Zig's modern features, such as safety and performance optimizations. This interoperability underscores one of Zig's standout characteristics, as it allows developers to gradually adopt Zig without discarding valuable C code. Overall, this example illustrates the ease with which Zig can function in tandem with C, enhancing its versatility in real-world applications. In summary, Zig presents a robust package for developers aiming for peak performance, safety, and productivity. Its straightforward syntax, efficient memory management, and focus on modularity create a powerful tool for both novice and expert programmers. The seamless interoperability with C and the impressive concurrency model further enhance its appeal, making it an attractive option for various development scenarios. So far, we've discussed Zig's performance and memory management, its safety features, concurrency model, modular programming, built-in package management, and interoperability with C having scratched the surface. I encourage you to dive deeper and experiment with Zig, exploring its capabilities for building robust applications. Zig is a modern and exciting programming language that combines performance, safety, and developer productivity. In today's lesson, we will explore the intricacies of Zig, its unique features, and practical examples that illustrate its power. Let's dive right in. Now let's explore how to manage memory manually in Zig, a critical feature that enhances performance and control. We begin by importing the standard library, which provides essential functionalities including memory allocation. Next, we initialize a memory allocator, here utilizing the page allocator from the standard library. The code proceeds to allocate 128 bytes of memory, which is a straightforward way to reserve space for data. After allocation, we use a loop to populate this buffer with values, demonstrating how to manipulate memory directly. This allows us to showcase the flexibility Zig offers in handling low-level operations. Subsequently, we print the contents of the buffer to observe the values we've assigned, illustrating a full cycle of allocation and utilization. Finally, we must remember to deallocate the memory we've allocated earlier. This is critical in Zig to prevent memory leaks. The call to free the buffer underscores the manual control Zig provides over memory management, which is vital in environments where resources are limited, such as embedded systems. By following these steps, you gain hands-on experience with Zig's manual memory management capabilities and learn to optimize memory usage effectively. Next, we will explore Zig's explicit error handling approach, which adds robustness to our code. In this code snippet, we define a function called mayFail that simulates an error by returning a value of type void, indicating it can either succeed or return an error. The use of the error union allows us to handle potential failures more transparently than traditional exception handling. Now let's see how we can implement error checking in the main function. Here we call mayFail and store the result in a variable. Following this, we utilize a switch statement to check the outcome of the function call. If an error occurs, specifically error, some error, we print an appropriate message to the console. If the operation is successful, we print a success message instead. This explicit control flow not only keeps the code clear, but also empowers developers to foresee and address errors proactively, enhancing overall reliability in software development. By absorbing this pattern, you can effectively manage errors in your applications, ultimately cultivating a more robust programming practice. Now let's see how we can implement concurrency in Zig using threads. In this example, we define a function called worker, which takes an identifier and an array to store results. Each worker will compute the square of its ID and store it in the corresponding index of the results array. Next, we move to the main function, where we initialize an array to hold the results initialized to 0 and an array of threads. We then use a loop to spawn 5 threads, each assigned to execute the worker function with its unique ID and a reference to the results array. This demonstrates how threads can be created and managed in Zig, harnessing its concurrency model effectively. Once all threads are spawned, we cannot forget to wait for them to complete their execution. A second loop is used for this purpose, where we call the join method on each thread, ensuring that the main program only proceeds once all threads have finished their calculations. Finally, we print the results, showcasing how easily multiple tasks can be executed concurrently in Zig, making it ideal for scenarios requiring simultaneous processing. Now let's take a look at how we can implement a basic math module in Zig, which will facilitate code reuse and organization within our projects. First, we define a new file named math.zig, where we create 2 public functions, add and subtract. The add function takes 2 integers a and b and returns their sum, while the subtract function computes and returns the difference between a and b. By declaring these functions as public, we allow them to be accessible from other files, promoting modular design. Next, we'll see how to utilize this math module in our main application. In the main.zig file, we begin by importing the standard library as well as our math module. Then we define the main function, where we can call the add and subtract functions from the math module. Here we store the results of both operations in variables sum and difference, respectively. Finally, we display the results using Zig's built-in debugging print function. This simple yet effective approach showcases how Zig's modular system enhances code organization and collaboration among developers. Now let's see how we can implement interoperability between Zig and C. The C code begins by including the standard library header, allowing us to use print for output. Within this code, we define a simple function called hello, which prints hello from C to the console when called. Next, we transition to our Zig code, where we start by importing the standard library. To access the C function, we use the extend C declaration for the hello function. This tells Zig that the function is implemented in C and allows us to call it directly from our Zig program. In the main function, we invoke the hello function, demonstrating how Zig can seamlessly integrate with existing C libraries. This strong interoperability feature is a significant advantage, especially for projects that involve legacy code, enabling developers to leverage C's vast ecosystem without compromising on Zig's benefits. By effectively combining these languages, developers can enhance productivity and facilitate smoother development cycles. This example encapsulates the power of Zig's design in allowing straightforward interaction with C code. Now let's take a look at a simple yet powerful example of Zig syntax. In this code, we declare a greeting string and print it to the console using the standard debugging output. This straightforward approach exemplifies how easy it is to get started with Zig. First, we import the standard library, which provides access to important functionalities. Then within the main function, we declare a constant named greeting, assigning it the value welcome to Zig. The clarity of this declaration is bolstered by Zig's type inference, allowing new developers to focus on their intentions without being bogged down by complex syntax. Next, we use std debug print to output our greeting to the console. The syntax is clean and effective, using a placeholder to specify where the value should be inserted, followed by a newline character to ensure the output is nicely formatted. This example not only demonstrates Zig's intuitive nature, but also highlights how its design promotes developer productivity, making it an ideal choice for both newcomers and seasoned programmers looking to streamline their workflows. Now that we've done a thorough exploration of Zig's features, it's important to contextualize this knowledge. Zig stands out not just for its performance and safety, but for its ability to enhance developer productivity. By combining these elements, Zig addresses common pitfalls encountered in other programming languages, making it an invaluable tool for developers. As we move forward, you'll find that mastering Zig opens doors to exciting projects. Whether you're working on system-level programs, game development, or any performance-critical applications, Zig provides the tools you need to excel. The journey doesn't end here. Keep experimenting with the language as you discover its nuances. In conclusion, Zig is a language poised to make a significant impact on the programming landscape. With its strong emphasis on performance, safety, and modularity, it offers everything developers need to build robust and efficient applications. By exploring Zig further and engaging with its community, you'll unlock endless possibilities and power your coding journey. Thank you for joining me today, and let's continue to learn and grow together in our programming industry. Zig is a general-purpose programming language designed with a focus on performance, safety, and developer productivity. Today, we're going to dive into the intricacies of Zig and explore its features, applications, and why it's becoming a popular choice among developers. So far, we've learned about Zig's philosophy of prioritizing performance, safety, and developer productivity. We've touched on its unique attributes like manual memory management and robust error handling. Today, however, we will explore its potential applications and how it can be leveraged in real-world scenarios. Now let's take a look at a simple example that illustrates how functions are defined and utilized in Zig. We begin by importing the standard library, which is essential for accessing built-in functionalities. Next, we define the add function, which accepts two integer parameters, a and b. It performs a straightforward operation, returning the sum of these two integers. This demonstrates how Zig allows us to create concise and efficient functions. Following the add function, we have the main function, marked with the pub keyword to indicate that it is publicly accessible. This function serves as the entry point for our program. Inside main, we invoke the add function with the integers 5 and 7, storing the result in a variable named result. Finally, we use the std debug print function to display the output in the console, showcasing Zig's clean and user-friendly syntax. This example not only highlights function definition and invocation, but also demonstrates Zig's capabilities for concise and readable code execution. Now let's see how we can implement manual memory management in Zig to gain better control over our program's resources. In the following example, we start by importing the standard library, which provides essential functionalities for our program. We declare the main function and use the page allocator from the standard library as our memory allocator. Next, we allocate an array of 10 bytes using allocator, alloc. This operation is wrapped in a try statement to handle any potential errors gracefully, ensuring that if allocation fails, our program can respond appropriately. The defer statement is particularly important here. It ensures that the allocated memory will be freed automatically once the main function exits, preventing memory leaks. We then proceed to initialize the allocated array using a loop, where each byte is set to its respective index value. This demonstrates not only how to fill the allocated memory, but also allows us to see that we can safely manipulate memory in Zig. Finally, we utilize std debug print to output the allocated memory, showcasing our allocation and initialization processes. This approach highlights Zig's commitment to safety and performance through manual memory management techniques. Next, we will implement a basic module to demonstrate how Zig's modularity enhances code organization and maintainability. We start with the math module, which encapsulates the multiply function. This function takes two integer parameters, a and b, multiplies them, and returns the result. By defining this functionality in a separate file, we clearly delineate its purpose, allowing for easy reuse across different parts of the code. Now let's take a look at how we utilize this math module in the main.zig file. Here we first import the standard library and the math module we just created. In the main function, we call the multiply function with specific arguments 4 and 5 and store the result in the result variable. This demonstrates how modular code can be clean and simple to use, as it abstracts away the details of multiplication. Finally, we print the product with a formatted output, showing that the separate module not only improves readability, but also makes the code easier to maintain as projects scale. This process of separating concerns is vital for effective software development. Now let's see how we can implement concurrency in Zig through the use of channels and asynchronous programming. In this code, we define a worker function that simulates a task by printing a message, pausing for a second to represent work being done, and then signaling completion via an auto-reset event. The std spawn function is key here. It allows us to run the worker function asynchronously without blocking the main execution flow, making it essential for high-performance applications. In the main function, an auto-reset event instance is initialized to serve as a signaling mechanism. This design enables us to manage task completion effectively. By spawning the worker in a separate thread, the main function can continue executing independently until it reaches the chan acquire call, which blocks execution until the worker signals that it is done. This pattern illustrates how Zig supports efficient task management and non-blocking I/O, making it a robust choice for applications that require multitasking and responsiveness. Now let's take a look at how we can directly call a C function from Zig, which exemplifies Zig's interoperability with C in this code. We first import the standard library to use its features, and then we declare an external C function, print, which allows us to print formatted output just like we would in C. Notice that the declaration includes the extend C keyword, specifying that this function follows the C calling conventions, essential for proper interaction with C libraries. Within the main function, we define a message string, hello from Zig, which we want to print. The print function is called directly with this message, showcasing how seamlessly we can leverage existing C functionality within our Zig programs. This direct call emphasizes the utility of Zig, allowing developers to utilize the extensive libraries and systems written in C without losing the advantages of Zig's safety and performance features. The simplicity of this call makes integration straightforward, enabling developers to enhance their applications by incorporating proven C code effectively. Now let's take a look at how we can leverage Zig's powerful built-in build system to create an executable. In this example, we define a build script that enables us to compile our main.zig file into an executable named myzigapp. The build function takes a pointer to a std build object, which provides us with the necessary tools for setting up our build configuration. By calling build_executable, we specify the name of the executable and the main source file. This function not only compiles the code, but also handles other essential aspects of the building process automatically. One of the standout features here is the exe install call, which ensures that the compiled executable is installed as part of the build process. This leads to a seamless deployment experience, allowing developers to focus more on coding without getting bogged down by complex build configurations. With this simple yet efficient setup, Zig streamlines the entire development workflow, making it accessible for both novices and experienced programmers alike. Now, developers can spend their time building applications rather than wrestling with the intricacies of project setup. In summary, Zig is an exciting programming language that balances performance with safety and developer productivity. Its robust feature set, including manual memory management, modular design, and support for concurrency, positions it as a powerful alternative in a landscape dominated by traditional choices like C or Rust. To recap what we've covered, we explored Zig's performance attributes, safe memory management practices, modular code organization, concurrency handling, and its interoperability with C. We also touched on the significance of an active developer community and highlighted the simplicity and effectiveness of its build system. As we continue our journey into the Zig programming language, there's so much more to uncover. Zig's straightforward syntax, coupled with a rich ecosystem of libraries and tools, make it a language worthy of attention for both novice and seasoned developers. Let's keep digging deeper into this intriguing language. In this final section, we will do a project challenge to apply what we have learned so far. Your task is to build a fully functional web application using the Zig programming language, which will allow you to demonstrate your understanding of Zig's concepts, project structure, and external libraries. Start by creating a well-organized directory for your application, including vital components like the zig.mod file for dependency management, the main application file, main.zig, for handling HTTP requests, and a routing file, routes.zig, to manage different endpoints. You will also implement a simple HTML template engine for rendering pages and ensure static files can be served from a designated directory. You are encouraged to document your code clearly, implement basic unit tests to validate functionality, and use Git for version control as you develop your project. Take this opportunity to integrate everything you have learned into a cohesive application that not only meets the outlined requirements but also showcases your unique approach. A thorough README (MD) file should accompany your submission, detailing setup instructions and any libraries used. For more information and guidance, please find the final project in the GitHub repository linked in the description.